Right now, as you listen to these words, a photon is completing a journey that began before the Earth existed. It left a place so distant that the light has been travelling for more than 2.5 billion years. Not metaphorically, not poetically, literally. A single packet of electromagnetic energy, a quantum of light, departed from a cosmic object designated PKS 14E135, when the most complex life forms on Earth were single-celled organisms drifting in primordial seas. The photon crossed the void while continents assembled and broke apart, while the atmosphere filled with oxygen, while fish crawled onto land, while dinosaurs rose and fell, while primates descended from trees and learned to speak and built telescopes and pointed them at the sky. And tonight, perhaps this very second, that photon strikes a detector, and something happens that will force us to rethink everything we thought we knew about time, about causality, about the relationship between the observer and the observed. The object it came from sits in the constellation Bootes, the herdsman, a patch of northern sky that ancient Greeks associated with a farmer driving oxen across the heavens. But there is nothing pastoral about what lurks there. PKS 14E135 is a Biel Lacerta object, a particular species of cosmic monster, a supermassive black hole at the heart of a distant galaxy, surrounded by a disk of superheated matter spiraling inward at nearly the speed of light, shooting twin jets of relativistic plasma directly along our line of sight. We are staring down the barrel of one of the most violent processes in the known universe. Astronomers first detected it in April 1981, a point of light flickering in radio wavelengths, unremarkable at first glance among the millions of distant objects catalogued by survey telescopes. But this one would prove to be something special. The redshift of PKS 1413+135 is measured at z equals 0.246. That number, dry and technical as it sounds, encodes an almost unbearable fact. When astronomers say an object has a redshift of 0.246, they mean that the wavelength of its light has been stretched by the expansion of the universe itself during the time the light was travelling, and that stretching tells us precisely how long the photons have been in flight. At this redshift, the light from PKS 1413+135 departed when the universe was approximately 10.7 billion years old, roughly 73% of its current age. The cosmos itself was younger then. Entire generations of stars had not yet been born. The Milky Way galaxy existed, but our solar system was nothing more than a diffuse cloud of gas and dust that would not begin to collapse for another 2 billion years. Try to hold that in your mind. A photon leaves its source. The universe is 10.7 billion years old. The photon travels through expanding space, through the void between galaxy clusters, through regions of intergalactic medium so diffuse that a cubic meter contains only a handful of atoms. It travels for 2.6 billion years. And when it arrives, the universe is 13.8 billion years old, and a species that has existed for less than a cosmic eye blink is waiting with instruments sensitive enough to catch it. But the journey's not a straight line. Between us and PKS 1413+135 lies another galaxy, a nearly edge-on spiral, tilted so we see it almost from the side, a Seyfert 2 galaxy at a slightly closer redshift of z equals 0.247. This intervening galaxy does something remarkable to the light passing by it. According to Einstein's general theory of relativity, mass warps the fabric of space-time, and light travelling through warped space-time follows curved paths. The galaxy acts as a lens, not a lens made of glass, but a lens made of gravity itself. The photons from PKS 1413+135 bend around the intervening mass, their paths deflected by the curvature of space. This is gravitational lensing, one of the most spectacular predictions of general relativity, confirmed by observation countless times since Arthur Eddington's famous 1919 eclipse expedition. But what happens at PKS 1413+135 is more subtle and strange. The lensing galaxy contains clumps of matter, perhaps globular clusters, perhaps smaller dark matter halos, with masses between 1,000 and 1,000,000 times that of our Sun. These objects create their own tiny lensing effects, what astronomers call millilensing. As the relativistic jets of the quasar shift and flicker, as knots of plasma move along the jet, they cross invisible lines in space called caustics, mathematical boundaries where the magnification from lensing changes abruptly. When a bright knot in the jet crosses a caustic, the light curve shows a characteristic signature, a U-shaped perturbation lasting about a year, followed by a symmetric feature appearing years later. Astronomers have identified 4 of these symmetric achromatic variability events in the monitoring data between 1980 and 2020. 4 times in 40 years, the geometry of cosmic masses aligned just so, and the light from an object 2.5 billion light-years away brightened and dimmed in patterns that encode the distribution of matter in a galaxy we have never visited and never will. And here is where the story takes a turn that no one expected. Those photons, the ancient travellers that crossed billions of years of cosmic time and bent around the warping mass of an intervening galaxy, those photons carry within them a secret about the nature of reality itself, a secret that a physicist named John Archibald Wheeler spent decades trying to articulate, a secret that, when finally tested, suggested something so radical that many scientists still refuse to accept its implications. The photons from PKS 1413+1135 do not arrive with their histories fully written. According to the mathematics of quantum mechanics, those photons exist in a state of superposition while they travel. They take, in some sense, multiple paths simultaneously. The gravitational lens offers them more than one route to Earth, and until the moment of detection, until the instant when a human-built instrument registers their arrival, the photons do not decide which path they took. The measurement that captures them, the choice of detector configuration, the experimental design selected by the physicists who built the telescope, these decisions, made here on Earth in the 21st century, reach backward through time and determine the history of a photon that began its journey before the planet existed. This is not mysticism, this is not metaphor, this is the straightforward implication of one of the most rigorously tested theories in the history of science. And to understand how we arrived at this impossible-sounding conclusion, we need to go back to the beginning, to a demonstration performed more than 2 centuries ago in a lecture hall in London by a polymath whose name has become synonymous with the mysteries of light itself. The year is 1801. George III sits on the throne of England, though his mind has begun its tragic descent into what contemporaries call madness. Napoleon Bonaparte is consolidating power across the Channel, and the intellectual classes of Europe are still processing the aftershocks of the Enlightenment, still drunk on the notion that human reason might unlock every secret of the natural world. In London, a physician and linguist named Thomas Young stands before the assembled members of the Royal Institution, about to demonstrate something that will take 2 centuries to fully understand. Young is 38 years old, though his accomplishments already span multiple lifetimes. He has contributed to the decipherment of Egyptian hieroglyphics. He has written treatises on the physics of vision. He speaks more than a dozen languages, and he has been thinking, obsessively, about the nature of light. The question had vexed natural philosophers for generations. Is light a wave, rippling through some invisible medium like sound ripples through air? Or is light composed of particles, tiny corpuscles streaming from luminous objects like bullets from a gun? Isaac Newton had favoured the corpuscular theory, and Newton's authority loomed so large that few dared contradict him even 50 years after his death. But Young suspected Newton was wrong. The apparatus is elegantly simple. Young allows sunlight to pass through a small hole in a screen, creating a single-point source of illumination. The light from this point then falls upon a second screen containing 2 narrow parallel slits, separated by a small distance. Beyond this second screen, a third surface waits to catch whatever pattern emerges. If light consists of particles, the logic seems straightforward. Particles would pass through one slit or the other, never both. They would strike the final screen in 2 clusters, one behind each slit, like bullets passing through gaps in a fence. But that is not what happens. Instead, the light creates a series of alternating bright and dark bands, an interference pattern. The same phenomenon occurs when 2 ripples meet in a pond. Where crest meets crest, the waves reinforce each other, and the water rises higher. Where crest meets trough, they cancel, and the water falls still. The interference pattern on Young's screen proves that light is behaving as a wave, spreading outward from each slit, the wavefronts overlapping and interfering with each other as they propagate toward the detector. Young presents his findings. The scientific establishment is, characteristically hostile. The corpuscular theory has Newton's imprimatur and Newton is sacred. Young is attacked in print, dismissed as a speculative amateur meddling in physics that properly belongs to mathematicians and experimentalists. But the interference pattern does not care about professional jealousies. It appears every time the experiment is repeated. And slowly, grudgingly, over the following decades, the wave theory of light gains acceptance. For a century, the matter seems settled. Light is a wave. Maxwell's equations describe its propagation. The luminiferous ether is hypothesized as the medium through which light waves travel, a ghostly substance filling all of space. And then, in the early 20th century, everything comes undone. The first crack appears in 1900, when Max Planck, trying to explain the spectrum of radiation emitted by hot objects, is forced to assume that energy comes in discrete packets, quanta. The second crack appears in 1905, when a young patent clerk in Switzerland named Albert Einstein explains the photoelectric effect by proposing that light itself is quantized, that it consists of particles now called photons. These are not the crude corpuscles Newton imagined. They are something stranger, something that defies the categories of classical physics. And when the double-slit experiment is performed again, this time with individual photons, fired one at a time, with enough delay between them that each photon passes through the apparatus alone, the interference pattern still appears. Think about what this means. A single photon is released. It passes through the screen with two slits. It strikes the detector on the other side. One photon, one impact, one discrete location where it lands. But if you perform this experiment thousands of times, marking where each individual photon strikes, the accumulated points form the same interference pattern that Young observed more than a century earlier. Each photon, travelling alone through the apparatus, behaves as though it is interfering with something. But there is nothing else there to interfere with except itself. The mathematics demands that we describe the photon as passing through both slits simultaneously, as existing in a superposition of two states, its probability wave spreading through both openings and interfering on the other side. The single point where the photon is finally detected is where the probability wave collapses into a definite outcome. But here is where the riddle turns malevolent. What happens if we try to catch the photon in the act? What if we place detectors at the slits, devices that register which opening the photon actually passes through? The moment we do this, the interference pattern vanishes. Now the photons behave like classical particles, passing through one slit or the other, never both. The accumulated marks on the final screen form two clusters instead of alternating bands. By observing which path the photon takes, we destroy the very phenomenon that proved it was taking both paths at once. This is not a matter of the detector disturbing the photon through some clumsy physical interaction. Niels Bohr, the Danish physicist who became the high priest of the new quantum theory, interpreted the result in terms of what he called complementarity. Wave behavior and particle behavior are complementary aspects of quantum systems. You can observe one or the other, never both simultaneously. The interference pattern is the signature of wave behavior. The which path information is the signature of particle behavior. And these two aspects are mutually exclusive. Bohr's explanation invoked Werner Heisenberg's uncertainty principle. Any measurement that determines which slit the photon passes through must involve an interaction that transfers momentum, and this momentum transfer, he argued, washes out the interference pattern. The act of observation isn't just revealing what was already there, it is changing the physical system being observed. For decades, this was the orthodox interpretation, taught in physics classrooms around the world. But it never fully explained the mystery. Later experiments by Marlon Scully and others challenged the neat story, suggesting that interference could be destroyed without any momentum transfer at all, that the mere availability of which path information was enough to collapse the pattern, regardless of whether the information was ever actually read by anyone. And beneath all the technical disputes lay a question that no one had satisfactorily answered. What is actually happening while the photon is in flight? Does it really pass through both slits? Does it exist in a superposition of paths, a smear of probability spread across space? And if so, what causes the superposition to collapse into a single, definite outcome at the moment of detection? Richard Feynman, who would go on to develop the modern formulation of quantum electrodynamics, was fond of declaring that all of quantum mechanics could be gleaned from carefully thinking through this one experiment. It contained, in miniature, every paradox, every interpretive nightmare, every metaphysical puzzle that the theory would ever generate. The double-slit experiment was not merely a demonstration of wave-particle duality. It was a crack in the foundations of reality itself, and it was a riddle that would not die. Every few years, another experiment pushed the boundaries further. Single electrons showed interference. Single molecules, clusters of dozens of atoms, showed interference. The scale of the quantum weirdness kept growing. And still, no one could say with certainty what was happening in between the source and the detector, what the particle was doing when no one was looking. The question was not settled philosophy. It was a live, contested physical problem, and it was about to become the obsession of one of the most creative minds in 20th century physics. John Archibald Wheeler was born on July 9, 1911 in Jacksonville, Florida, the son of librarians. Joseph and Mabel Wheeler, she went by Archie, raised their son in homes filled with books, and young John developed early the habit of voracious reading that would define his intellectual life. He was brilliant from the start, the kind of child who makes teachers nervous, who asks questions that have no easy answers. By the age of 21, he had earned a doctoral degree in physics from Johns Hopkins University. 21 years old, and already he had penetrated to the research frontier of one of the most demanding fields of human knowledge. But the degree was only the beginning. The young Dr. Wheeler had larger ambitions. He wanted to understand the universe at its deepest level, to discover, as he would later put it, the deep, happy mysteries that lay beneath everything else. He went to Copenhagen. In the 1930s, the city on the Øresund was the undisputed capital of the quantum world. Niels Bohr presided there, having established the Institute for Theoretical Physics as a pilgrimage site for anyone serious about understanding the new physics. The greatest minds of the era, Heisenberg, Pauli, Dirac and countless others, passed through Copenhagen, arguing, collaborating, wrestling with the implications of a theory that seemed to work perfectly while making no sense whatsoever. Wheeler arrived and found himself in the presence of giants. Bohr took him seriously, engaged with his ideas, treated the young American as a colleague rather than a student. The two men began a collaboration that would shape Wheeler's thinking for the rest of his life. Together, they wrote the original paper explaining the mechanism of nuclear fission, the splitting of the atomic nucleus that would soon change the course of history. Wheeler was not merely a witness to the birth of the atomic age, he was one of its midwives. When the war came, Wheeler joined the Los Alamos Scientific Laboratory, working under Oppenheimer on the Manhattan Project. After the war, he played a central role in the development of the hydrogen bomb, the thermonuclear weapon that made atomic bombs look like firecrackers. Some of his colleagues never forgave him for this. Wheeler never apologized. He was a patriot who believed his country needed these weapons to survive, and he lived with the weight of that belief for the rest of his life. But the bombs were never his true passion. Wheeler's heart belonged to the deep questions, the nature of space-time, the meaning of quantum mechanics, the ultimate laws that governed everything. He returned to Princeton after the war and began building what would become one of the most influential careers in theoretical physics. In 1957, Wheeler introduced the term wormhole to describe hypothetical tunnels through space-time, shortcuts connecting distant regions of the universe. The concept had been lurking in the mathematics of general relativity for years, but Wheeler gave it a name, made it vivid, turned it into something physicists could argue about at conferences and scribble on blackboards. And then, on December 29, 1967, Wheeler stood before a joint audience of the Sigma Xi and Phi Beta Kappa societies to deliver a lecture titled Space and Time. During that talk, he used a term that had been floating around among astronomers and theorists, a term for those collapsed stellar remnants whose gravity was so intense that not even light could escape. He called them black holes. The written version of the lecture was published the following spring, and the name stuck. Wheeler had given the universe one of its most evocative images, a phrase that would enter the popular imagination and never leave. Wheeler was not merely a physicist, he was a phrasemaker, a storyteller, a man who understood that ideas needed to be dressed in memorable language before they could capture the mind. His coinages spread through the field like wildfire because they were not just labels, they were invitations to wonder. He also had a gift for mentoring. Throughout his career at Princeton and later at the University of Texas at Austin, where he served as director of the Center for Theoretical Physics until 1986, Wheeler nurtured the talents of young theorists who would go on to reshape physics. Among his students was Richard Feynman, who would become the most charismatic physicist of his generation, who would win the Nobel Prize and write best-selling books and become a cultural icon. Feynman never forgot what he owed Wheeler. Few of Wheeler's students did. But beneath the wordplay and the mentorship and the administrative duties, Wheeler was consumed by something else, a deep, persistent unease about the foundations of quantum mechanics. He had learned the theory from Bohr himself. He had internalized the Copenhagen interpretation, the complementarity principle, the notion that we should not ask what the particle is really doing when we are not looking. But Wheeler could not stop asking. The equations worked. The predictions matched experiment to astonishing precision. Quantum electrodynamics, the theory Feynman helped develop, could calculate the magnetic moment of the electron to 12 decimal places, a level of accuracy unmatched in any other field of science. But what did the equations mean? What was the theory telling us about the nature of reality? Wheeler discussed these questions with Einstein himself, whose office at the Institute for Advanced Study was just a short walk from Wheeler's base at Princeton. Einstein famously hated the Copenhagen interpretation. He never accepted that God plays dice with the universe, as the quip went. He spent the last decades of his life searching for hidden variables, for some deeper deterministic theory beneath the apparent randomness of quantum mechanics. Wheeler listened, argued, learned, and eventually he concluded that Einstein was wrong. Not about the importance of the questions, but about the answers. The mystery was not a flaw to be patched. The mystery was the message. Quantum mechanics was trying to tell us something profound about the relationship between observer and observed, about the role of measurement in bringing reality into being. And Wheeler was determined to find out what. He developed a habit of posing thought experiments, not practical proposals for laboratory apparatus, but conceptual tests designed to sharpen the issues, to force the theory to show its hand. He was probing the boundaries, looking for places where the standard interpretation creaked under pressure, where the cracks might reveal something deeper beneath. The experiments he imagined shared a common characteristic. They were designed to ask questions that the theory seemed to forbid. Questions about what happened in the gaps, in the dark spaces between preparation and measurement. Wheeler wanted to shine a light into regions that Bohr had declared off-limits. He wanted to know what the photon was doing while no one was watching, and he developed an image, a metaphor, to capture the essence of the quantum riddle. He called it the Great Smoky Dragon. "Picture a dragon," Wheeler would say. "You can see its tail clearly at one end. That's where the photon is emitted, where the quantum system is prepared. And you can see its head clearly at the other end. That's where the photon is detected, where the measurement occurs. But the body of the dragon, the part between emission and detection, is hidden in smoke. You cannot see it. The theory refuses to tell you what is there. You can measure the tail and the head with perfect precision, but you must never ask what the dragon's body looks like. This was the Copenhagen bargain. Accept that some questions have no answers, and the theory will reward you with predictions of supernatural accuracy. Ask forbidden questions, and the theory turns silent." Wheeler was not willing to accept the silence. He kept designing thought experiments that pushed against the smoke, that tried to force the dragon to reveal itself. And in the late 1970s, he constructed one that would prove to be the most disturbing of all. What if, Wheeler asked, we delay our choice of measurement until after the photon has already passed through the apparatus? What if we wait until the photon has committed to its path, or to both paths, or to whatever strange superposition the theory demands, and only then decide whether to look for interference or to ask which path it took? The thought experiment was elegant in its cruelty. If the photon really chooses its path at the slits, then a later measurement cannot affect an earlier event. Cause must precede effect. The universe cannot run backward. A decision made after the fact cannot reach into the past and change what already happened. But quantum mechanics, Wheeler realized, said otherwise. The equations made a clear prediction. The photon's behavior would depend on how it was detected, regardless of when that detection took place. If you set up your apparatus to look for interference, you would find interference. If you set up your apparatus to determine which path the photon took, the interference would vanish. And this would be true even if you made your choice after the photon had traversed the distance between the slits and the detector. Even if you made your choice, in principle, billions of years after the photon began its journey. Wheeler called it the delayed choice experiment, and in the version that would come to haunt physicists for generations, he imagined performing it not with photons in a laboratory, but with light from the depths of space. Light that had been travelling for eons, light that had been gravitationally lensed around distant galaxies, light whose path had apparently been fixed long before the Earth existed. In this cosmic version, the choice of detector configuration, the decision made by human beings on a small rocky planet, would reach backward through time and determine whether photons that left their source billions of years ago had travelled one path or two. The past, Wheeler suggested, might not be as fixed as we assumed. The history of the universe might remain open, might be shaped by measurements yet to be made, might depend on observers who did not exist when the events in question occurred. It was a staggering idea. It seemed to violate everything we thought we knew about causality, about time, about the distinction between past and present. And Wheeler offered it not as mysticism, not as philosophy, but as the straightforward implication of the most rigorously tested theory in the history of science. The Great Smoky Dragon was not merely hidden. Its body was undetermined, not just unknown to us, but not yet decided by the universe itself. And the decision, when it came, would be made not at the moment of emission, but at the moment of detection. The measurement would create the history. Wheeler died in 2008 at the age of 96. He had lived long enough to see his thought experiment translated from philosophical provocation to laboratory reality, long enough to see the first tentative confirmations that the delayed choice effect was real, that the implications he had drawn were not artifacts of misinterpretation, but genuine features of the quantum world. He had spent his life asking forbidden questions, and in the end, the universe had answered. But the answers raised questions more troubling still. The apparatus Wheeler designed in his mind was deceptively simple. Strip away the cosmic drama, the billions of years, the existential vertigo, and what remains is a puzzle you can diagram on a napkin. 4 mirrors, 2 beam splitters, 2 detectors, and a single photon. That is all it takes to break causality. The device is called a Mach-Zehnder interferometer, and its operating principle dates to the 19th century, long before anyone imagined using it to interrogate the nature of time. 2 beam splitters and 2 mirrors create a closed loop through which light can travel. A photon enters through the first beam splitter and is divided, not into 2 weaker photons, but into a superposition of taking both paths simultaneously, a quantum state that has no classical analogue. The photon, in some sense that defies ordinary language, travels through the upper arm of the interferometer and through the lower arm at the same time. The 2 paths converge at the second beam splitter, where they either recombine into a single output or split again toward 2 detectors, depending on the precise geometry of the apparatus. When the second beam splitter is in place, the 2 paths interfere. The photon's quantum amplitude along one path adds to or subtracts from its amplitude along the other, and the result is a detection pattern that depends on the phase, relationship between the 2 arms. Adjust the path lengths, and you can send the photon to one detector with certainty, or split its probability evenly between both, or achieve any ratio in between. This is the signature of wave behavior. The photon has traveled both paths, and the information from both paths combines to determine the outcome. The interference pattern is proof that the photon was, in some meaningful sense, everywhere at once. But remove the second beam splitter, and the situation changes utterly. Without that final recombination, the 2 paths do not interfere. The photon arrives at one detector or the other with 50-50 probability, and whichever detector clicks tells you unambiguously which path the photon took. The upper path leads to one detector, the lower path leads to the other. There is no interference, no superposition at the moment of detection, no evidence that the photon was ever in 2 places at once. The detection event reveals a particle that travelled a single definite trajectory. 2 configurations of the same apparatus, 2 mutually exclusive behaviours, wave or particle, both paths or one path. And the only difference is whether a half-silvered mirror sits at the far end of the interferometer when the photon arrives. Now here is where Wheeler's genius, or his cruelty, depending on your temperament, becomes apparent. The first beam splitter, the one that creates the initial superposition, does its work the instant the photon enters the apparatus. The photon passes through and begins its journey down the 2 arms, a journey that might take nanoseconds in a tabletop experiment or, as Wheeler would later imagine, billions of years in the vastness of intergalactic space. The second beam splitter, the one that determines whether wave or particle behaviour will be observed, sits at the far end. And Wheeler's proposal was this: wait until the photon has already passed through the first beam splitter, wait until it has already begun travelling both paths, or one path, or whatever it is that photons do between measurements, and only then decide whether to insert the second beam splitter. Make the choice after the photon is already in flight. Make the choice after the photon has, by any classical reckoning, already committed to its trajectory. Make the choice at the last possible instant, when the photon is already bearing down on the final mirrors, already nanoseconds from detection. The mathematics of quantum mechanics does not care about this delay. The prediction is unambiguous. If you insert the second beam splitter at the last moment, you will observe interference. The photon will behave as though it had travelled both paths. If you leave the second beam splitter out, you will observe which path information. The photon will behave as though it had travelled only one path, and this will be true regardless of when you make your decision, regardless of whether the photon is still at the first beam splitter, or halfway through the apparatus, or a femtosecond from striking the detector. The timing does not matter. The decision reaches backward. Wheeler posed the question with characteristic directness. Can one choose whether the photon shall have come through both of the slits, or only one of them, after it has already traversed the screen? The phrasing was careful and its implications were staggering. If the answer is yes, and quantum mechanics insist that the answer is yes, then the choice made at the moment of detection determines something about the photon's past. Not merely reveals something that was already true, but determines it, as if the past had been waiting for the present to give it definition. This was not, Wheeler insisted, a trick of language. This was not a failure of human intuition that could be dissolved by more careful thinking. This was a genuine prediction of the theory, a prediction that would have to be verified or refuted by experiment, and if verified, it would mean something profound about the relationship between measurement and reality, between the present and the past, between the observer and the observed. Wheeler put it bluntly in 1978, when he first presented the delayed choice concept in its full form. He argued that it is wrong to attribute a tangibility to the photon in all its travel, from the point of entry to its last instant of flight. The photon does not have a trajectory. It does not have a definite path. It does not have any property at all until a measurement is made, and the measurement, whenever it occurs, reaches back and defines what the photon was doing all along. The Great Smoky Dragon was not merely hidden from view. Its body was undetermined, not just unknown, but not yet decided, and the decision would be made not at the source, not at the slits, not at any point along the photon's journey, but at the detector. The measurement would create the history. In 1978, Wheeler described 7 different variations of the delayed choice experiment, each designed to probe a different aspect of the quantum puzzle. Some involved double slits, others involved interferometers, still others involved even more exotic configurations. But the version based on the Mach-Zehnder interferometer became the canonical form, the simplest to analyse mathematically, the clearest in its implications. A photon enters. A beam splitter creates a superposition. The photon travels. The experimenter waits. The experimenter decides. The second beam splitter is inserted or removed. The photon is detected, and the detection reveals a history, wave or particle, both paths or one path, that appears to have been shaped by the experimenter's choice. Wheeler knew what he was claiming. He knew that it sounded like mysticism, like a violation of everything physics was supposed to be about. But he was adamant. This was not philosophy, not wordplay, not an artifact of imprecise thinking. This was a testable prediction. The delayed choice effect, if real, would be a genuine retrocausal signature, a case where the present reaches back and touches the past. And Wheeler believed it would be real. He believed that when physicists finally built the apparatus and ran the experiment, they would find exactly what quantum mechanics predicted. They would find that the choice made after the photon was in flight determined what kind of thing the photon had been all along. The thought experiment sat in the literature like an unexploded bomb. It was radical, it was disturbing, and it was, for the moment, purely theoretical. The technology to perform a true delayed choice experiment, to make the decision faster than any signal could travel from the first beam splitter to the point of decision, to close the loopholes that classical explanations might exploit, did not yet exist in 1978. Wheeler had handed his colleagues a puzzle that they could not yet solve experimentally, a challenge that they could not yet meet. And so, for a time, the physics community did what it often does when confronted with conceptual threats. It filed the problem under interesting but not urgent, and returned to more tractable work. But the bomb did not go away. It sat there, waiting. And the question it posed grew only more insistent with time. If the delayed choice effect was real, if the present genuinely shapes the past, then what did that mean for our understanding of causality? What did it mean for our understanding of time? What did it mean for the picture of the universe that physics had spent centuries constructing? The question Wheeler had asked in 1978 was not merely technical, it was existential, and the physics community, whether it admitted it or not, had no idea how to answer it. The silence that followed Wheeler's proposal was not, strictly speaking, silence. Papers were written, lectures were given. The delayed choice thought experiment entered the textbooks and the popular science books and the philosophical literature. But the conceptual crisis that Wheeler had tried to provoke did not materialize. The physics establishment absorbed his challenge without crisis, and the mechanism of that absorption tells us something important about how science manages its foundational anxieties. The shield was called the Copenhagen interpretation, and it had been forged half a century earlier in the debates between Niels Bohr and Albert Einstein. Copenhagen was not so much a physical theory as a set of rules for avoiding certain questions. It declared that quantum mechanics was complete, that the wave function contained all the information there was to have about a quantum system, and that asking what a particle was really doing between measurements was a meaningless question. The formalism gave probabilities for experimental outcomes. The formalism was spectacularly successful, and the formalism, according to Copenhagen, was all there was. Under Copenhagen's rules, the delayed choice experiment posed no paradox at all. If asking what the photon really did before measurement is a meaningless question, then the apparent retrocausal implication simply does not arise. There is no fact about whether the photon travelled one path or two until a measurement creates that fact. The experimenter's choice does not reach back and change the past, because there is no past to change, not in the sense of a definite sequence of events that occurred whether or not anyone was watching. The past, in the Copenhagen view, is just another name for correlations between present records. It is not a thing that exists independently of observation. Wheeler himself articulated this view with characteristic vividness. The past has no existence except as it is recorded in the present. This was not a concession that Copenhagen had defeated his thought experiment. It was the point Wheeler was trying to make. The past is not fixed. The past is not out there waiting to be discovered. The past is constructed by measurements, and those measurements occur in the present. The delayed choice experiment was not a paradox to be explained away. It was a demonstration of a deep truth about the nature of reality. But here is where the intellectual dodge occurred. Most physicists were not interested in deep truths about the nature of reality. Most physicists were interested in calculating cross-sections and predicting energy levels and designing experiments that would yield Nobel Prizes. Copenhagen gave them permission to do exactly that. It told them that the foundational questions were not merely difficult but meaningless, that the appearance of paradox was a kind of philosophical illusion, that the correct response to Wheeler's challenge was not to grapple with its implications but to shrug and return to the equations, shut up and calculate. The phrase was coined in frustration by David Mermin, who meant it as a criticism of physics culture, but it became an unofficial motto of the discipline. Copenhagen provided the intellectual cover. The wave function evolves according to the Schrödinger equation. Measurements collapse the wave function to an eigenstate. The Born rule gives the probability of each outcome. These rules work. They generate predictions that match experiment to extraordinary precision. Why ask what they mean? The delayed choice experiment was absorbed into this pragmatic framework without rupture. Textbooks presented it as an illustration of quantum weirdness, a vivid demonstration that our classical intuitions do not apply at the microscopic scale. Popular science books described it as evidence for the strange and wonderful nature of quantum mechanics. But the conceptual knife that Wheeler had tried to insert into the foundations of physics was blunted by the Copenhagen shield. The experiment did not provoke a crisis because Copenhagen had, decades earlier, inoculated the discipline against precisely this kind of crisis. Questions about the nature of reality, about the relationship between observation and existence, about whether the past was fixed or open, these were philosophical questions, not physical ones, and Copenhagen had declared them out of bounds. The result was a strange intellectual situation. The most rigorously tested theory in history seemed to imply that the present could reach back and shape the past. The founder of that implication, one of the most respected physicists of his generation, insisted that the implication was genuine and profound. But the community of physicists who use that theory every day declined to take the implication seriously. They had their predictions, they had their experiments, they had their Nobel Prizes, and they had Copenhagen to assure them that the deep questions did not need answers. Wheeler found this situation intolerable. He had studied under Bohr. He understood Copenhagen as well as anyone alive. But he did not believe that Copenhagen was the final word. He did not believe that the foundational questions were meaningless. And he spent the last decades of his life trying to force those questions back into the conversation, trying to provoke the crisis that Copenhagen had suppressed, trying to make physicists confront the implications of their own theory. His approach was relentless. He gave lectures, he wrote papers, he coined phrases, it from bit, law without law, the participatory universe, designed to crystallize his vision and make it impossible to ignore. He insisted that physics was not just a machine for generating predictions, but a window onto the nature of reality. And he insisted that the reality revealed by quantum mechanics was stranger than anyone had admitted, stranger than Copenhagen had allowed, stranger perhaps than human beings were equipped to understand. The universe, Wheeler argued, is not made of things. It is made of answers to questions. Every measurement is a question posed to nature, and every outcome is an answer. But the answer does not exist until the question is asked. And the question, when asked, reaches back through time and defines what was always true. This was not mysticism. This was the plain reading of the quantum formalism taken seriously, pushed to its logical conclusion. But the physics community, for the most part, was not ready to take that reading seriously. Copenhagen offered an easier path. It offered a way to use the formalism without confronting its implications, a way to get the right answers without asking what those answers meant. And for decades, that was enough. The delayed choice experiment sat in the literature, acknowledged but not absorbed, discussed but not confronted. The dragon remained smoky. The past remained officially closed. And yet the question would not die. It could not die, because it was built into the structure of the theory itself. Every time a physicist calculated an interference pattern, every time an experimentalist adjusted a beam splitter, every time a student learned the rules of quantum superposition, the delayed choice question was lurking beneath the surface. The present shapes the past. The measurement creates the history. The observer is not separate from the observed. Wheeler kept insisting. He kept designing thought experiments. He kept pushing against the comfortable consensus. And eventually, as technology advanced, as experimentalists developed new tools and techniques, the thought experiment began to edge toward reality. The bomb that Wheeler had planted in 1978 was still sitting in the foundations of physics, and sooner or later someone was going to figure out how to detonate it. The tension between Wheeler's vision and Copenhagen's silence was not merely technical. It was a tension between two conceptions of what physics was supposed to be about. Copenhagen saw physics as a set of recipes for predicting experimental outcomes, and it saw questions about underlying reality as either meaningless or unanswerable. Wheeler saw physics as an inquiry into the nature of existence, and he saw the quantum formalism as evidence for a reality far stranger than anyone had dared to imagine. The recipes were useful, yes. The predictions were accurate, yes. But they were not the point. The point was understanding what the universe actually was. This disagreement ran deeper than methodology. It was, at its heart, a disagreement about the purpose of human inquiry. Copenhagen offered closure. It told physicists that they had done their job when they had generated accurate predictions, that the remaining questions were not physics questions at all, that the desire for a deeper understanding was a vestige of classical intuitions that quantum mechanics had rendered obsolete. Wheeler offered something else, an invitation to continue asking, to keep probing, to follow the implications of the theory wherever they led, even if they led to conclusions that seemed impossible. The delayed choice experiment was Wheeler's most pointed challenge to the Copenhagen consensus. It took the standard quantum rules, superposition, interference, measurement, and arranged them in a configuration that made the retrocausal implication unavoidable. If the choice made at the detector determines what kind of thing the photon was on its journey, then either the present shapes the past, or there is no past to be shaped, or something even stranger is going on that no one had yet articulated. Copenhagen could deflect the first option by embracing the second, but even that embrace had radical implications that most physicists preferred not to examine. What does it mean to say that the past has no existence except as it is recorded in the present? What does it mean to say that there is no fact about what the photon did until a measurement creates that fact? These are not trivial claims. They are claims about the structure of time, about the nature of causality, about the relationship between mind and matter. They are claims that, taken seriously, would require a fundamental revision of our picture of the world. But taking them seriously was precisely what the physics community had trained itself not to do. Copenhagen had been designed to prevent existential vertigo. It had been designed to let physicists get on with their work without being paralyzed by foundational anxieties. And it had succeeded, perhaps too well. The delayed choice experiment revealed how thoroughly that training had taken hold. Wheeler could propose his thought experiment, could publish his arguments, could lecture and write and insist, and the community could nod and move on, secure in the knowledge that Copenhagen had already handled the problem. The handle was simple: don't ask. The photon doesn't have a definite path before measurement. The question of which path it took is not a meaningful question. The delayed choice effect is just quantum mechanics being quantum mechanics, strange and wonderful and fundamentally resistant to classical interpretation. There is no retrocausal paradox because there is no classical reality for the present to reach back and disturb. But Wheeler knew that this handle was not an answer. It was a refusal to answer. It was a sophisticated, philosophically defended refusal, but it was a refusal nonetheless. And Wheeler spent his remaining years trying to force the physics community past that refusal, trying to make it confront the thing it was avoiding, trying to open a conversation that Copenhagen had closed. The conversation would eventually open, but not in Wheeler's lifetime. The technology would advance. The experiments would become possible. The loopholes would be closed one by one until the delayed choice effect could no longer be dismissed as a theoretical curiosity. And when that happened, when the bomb finally detonated, the physics community would be forced to reckon with the question Wheeler had posed in 1978. Does the present shape the past? Is the history of the universe open or closed? And what does it mean to live in a cosmos where the answer to that question depends on measurements that have not yet been made? Wheeler died in 2008. He did not live to see the full flowering of delayed choice experiments, did not live to see his cosmic version tested on light from distant quasars, did not live to see the retrocausal signature confirmed across billions of years. But he had planted the seed. He had asked the question, and the question, once asked, could not be unasked. It sat in the foundations of physics, waiting for experimentalists to catch up with theory, waiting for the technology to mature, waiting for someone to take the thought experiment and make it real. The great smoky dragon was still hidden, its body was still undetermined, but the question of when that determination would occur, and what it would mean for our understanding of time and causality and the nature of the past, was now inescapable. The silence could not hold forever. Sooner or later, someone would have to listen, and someone did. The first to listen were the experimentalists, the careful hands who could translate Wheeler's philosophical provocation into glass and mirrors and precisely timed electronics. The thought experiment had been on the table since 1978, a challenge issued to anyone bold enough to attempt what Wheeler himself admitted seemed impossible: to change the configuration of the apparatus after the photon had already made its choice, if choice was even the right word, and to do it fast enough that no signal could pass between entry and exit. No classical information could leak, no hidden variable could anticipate the experimenter's decision. The challenge was not merely technical, it was a challenge to the very notion that the experiment could be performed at all. For the Mach-Zehnder interferometer to work as Wheeler imagined, the distances had to be short enough that the photon's transit time was measurable, but the switching had to be faster than that transit time. You had to decide whether to insert the second beam splitter after the photon was already inside the apparatus, but before it reached the position where that beam splitter would or would not be waiting. In 1978, that seemed absurd. Photons move at the speed of light. The apparatus would have to be large enough to give you time to switch, but the switching mechanism would have to be faster than anything electronic circuits could manage. The loophole Wheeler himself had identified was obvious. If the experimenter decides in advance, even unconsciously, even through some subtle correlation in the apparatus, the delayed choice effect becomes meaningless. The photon could, in principle, have been informed by some classical channel. The test requires genuine randomness, genuine separation, genuine surprise. Carroll Alley understood this. A professor at the University of Maryland, College Park Alley, had spent his career at the intersection of optics and precision measurement. He had worked on laser ranging to the moon, bouncing light off retroreflectors left by Apollo astronauts, and timing the returns to millimeter accuracy. He knew how to handle photons, he knew how to think in nanoseconds, and he recognized that Wheeler's delayed choice experiment was not just a philosophical puzzle, but a technical challenge that might, with enough care, be met. The work began in the first half of the 1980s. Alley and his colleagues constructed an interferometer that allowed a photon to take either one path or two after passing through the initial beam splitter. The key innovation was speed. They needed to switch the configuration of the apparatus between the moment the photon entered and the moment it would reach the decision point, and they needed to do this in a way that was genuinely random, genuinely unpredictable, genuinely independent of anything the photon might have encountered on its way in. The physics community watched with interest and skepticism. Wheeler's thought experiment had been discussed for years, analysed and reanalyzed, defended and attacked. But until someone actually built the thing and ran the test, it remained theoretical. Alley's work changed that. In 1986, the pioneering realization was reported. The details were technical, the apparatus complex, the results provisional. But the essential finding was clear. The delayed choice effect was real. When the configuration was switched after the photon entered the interferometer, the outcome depended on the configuration at the moment of measurement, not on any prior state of the apparatus. The photon behaved as if its path had been determined by the final setup, even though that setup had been chosen after the photon's journey began. The quantum mechanics worked exactly as Wheeler had predicted. The history of the photon, or what we would classically call its history, was not fixed at entry, it was fixed at exit. But Alley's experiment, for all its ingenuity, left loopholes. The switching was fast, but not fast enough to satisfy the strictest critics. The randomness was good, but not perfect. The apparatus was small, the transit times short, the margins thin. Someone could always argue that some subtle classical correlation had slipped through, that the experiment had not truly closed the door on hidden variable explanations or predetermined outcomes. The delayed choice effect had been demonstrated, yes, but had it been proven? Had every loophole been sealed? The answer would come 2 decades later from Paris. Vincent Jacques was a young physicist working in the laboratory of Jean-François Roch at the École Normale Supérieure de Cachan. The field had advanced considerably since Alley's pioneering work. Quantum optics had become precise, controlled, and capable of single photon manipulation with extraordinary fidelity. And Jacques had access to something Alley had not: a quantum random number generator. The significance of this tool cannot be overstated. In Alley's experiment, the switching decision had been made by electronic circuits that, however fast, were still classical systems. In principle, they could be predicted. In principle, some hidden variable could have known what they would do. But a quantum random number generator derives its randomness from quantum events themselves, from the inherently unpredictable decay of radioactive atoms or the equally unpredictable outcomes of photon measurements. There is no hidden variable that can anticipate the output of such a device. The randomness is fundamental. The decision is genuinely undetermined until it is made. Jacques and his colleagues constructed their interferometer with meticulous care. A single photon was sent into the apparatus, passing through the first beam splitter and entering the 2 possible paths. After the photon had entered, after it had, in some sense, already begun its journey through both arms of the interferometer, or through one of them, depending on how you chose to describe it, the quantum random number generator made its decision. Insert the second beam splitter or leave it out. The choice was relativistically separated from the photon's entry. There was no way, even at the speed of light, for information about the configuration to have reached the photon before it made its apparent decision about which path to take. The results appeared in Science on February 16, 2007. The paper ran 3 pages. The implications ran deeper. The curious feature was precisely the one Wheeler had predicted. The timing of the decision did not affect the results. Whether the second beam splitter was present or absent was decided after the photon had already split, in the quantum sense, into the superposition of both paths. Yet the photon's behaviour at the detectors depended entirely on that later decision. Insert the beam splitter, and interference appeared. The photon had travelled both paths simultaneously, its wave function recombining at the exit to produce the characteristic pattern of constructive and destructive probabilities. Remove the beam splitter and interference vanished. The photon had travelled one path or the other, and the detector recorded a clean, definite arrival with no trace of superposition. The experiment was reproducible. The experiment was peer-reviewed. The experiment was, by the standards of quantum optics, clean. And yet the critics remained, because the critics had one final objection, one last refuge of skepticism. The photon's journey through the interferometer lasted nanoseconds, billionths of a second. The delayed choice reached back in time, yes, but it reached back such a tiny distance that the word back almost seemed like an exaggeration. What did it mean to say the present shapes the past when the past in question was so recent it might as well have been the present? The retrocausal effect was real, but it was small. The photon left the source and arrived at the detector almost instantaneously by human standards. The delay between entry and measurement was measured in nanoseconds. The delay between the quantum random number generator's decision and the photon's arrival at the beam splitter was measured in nanoseconds. This was not what Wheeler had in mind. Wheeler had imagined something grander. He had imagined reaching back not nanoseconds but eons. He had imagined testing the delayed choice effect on photons that had been travelling for billions of years. Photons whose history, if history was even the right word, stretched back to an era when the Earth did not exist, when the sun had not yet formed, when the atoms that would become our bodies were still scattered through interstellar gas. If the present could shape the past, let it shape a past that truly deserved the name. Let it reach back far enough that the retrocausal effect became undeniable, far enough that no quibble about nanoseconds could diminish its significance. And here, the universe provided an unexpected gift. Because nature, it turned out, had already built the apparatus Wheeler needed. It had built an interferometer on cosmic scales, using the curvature of space-time itself as the optical element. It had split photons from distant quasars around massive galaxies and sent them on diverging paths that reconvened, billions of years later, at a tiny blue planet where physicists with mirrors and detectors were waiting to receive them. The phenomenon is called gravitational lensing. It was predicted by Einstein's general theory of relativity, implicit in the bending of space-time around massive objects. A ray of light passing near a star or galaxy does not travel in a straight line. It follows the contours of space-time curving around the mass, deflected by geometry rather than by any physical contact. The effect is subtle for ordinary stars. It becomes dramatic for galaxies and galaxy clusters, where the accumulated mass of billions of stars and trillions of solar masses of dark matter can bend light through measurable angles, distorting the images of background objects, stretching them into arcs and rings, and, in certain fortunate alignments, splitting them into multiple copies. The first confirmed gravitational lens was discovered in 1979. Dennis Walsh, Robert F. Carswell, and Ray J. Wayman were observing with the 2.1-meter telescope at Kitt Peak National Observatory in Arizona when they noticed something peculiar. 2 quasars, separated by roughly 6 seconds of arc, with identical spectra and identical redshifts. 6 arc seconds is not much, the same as the apparent size of a compact disc viewed from 4 kilometers away, but it was enough to be resolved. The question was immediate. Were these 2 different quasars that happened to look identical, or were they 2 images of the same quasar split by something lying between? The answer came quickly. The double quasar, designated Q0957+1, was one object seen twice. The lensing agent was a massive elliptical galaxy designated Cauchy-1, lying in a cluster at redshift 0.36, roughly 4 billion light-years from Earth. The background quasar sat at redshift 1 before 15, much farther away, its light having travelled across more than half, the observable universe before encountering the lens. And when that light encountered the lens, it did not simply bend, it split. Some photons curved around the left side of the galaxy, some curved around the right. They took different paths through space-time, traversed different regions of the universe, experienced different gravitational delays, and then, billions of years later, they converged again, not because anything brought them together, but because the geometry of space-time and the position of the observer conspired to bring them to the same destination. Earth's telescopes, pointed at the sky, received light from the same quasar by two different routes, arriving as two distinct images separated by 6 arc-seconds of apparent sky. The analogy to an optical lens is imperfect but useful. A glass lens bends light by changing its speed. Photons travel more slowly through glass than through air, and the curved surface of the lens forces them into new trajectories. A gravitational lens bends light by changing the shape of space itself. The photons still travel at the speed of light, still follow geodesics, still take the straightest possible path through space-time. But space-time is curved around the mass, and the straightest possible path through curved space is not a straight line by Euclidean standards. The effect is lensing without glass, focusing without material, optics written into the fabric of the cosmos. And here is where Wheeler's vision becomes more than metaphor. A gravitational lens does not merely produce multiple images. When the geometry is right, when the alignment is close enough, it produces something startlingly similar to the double-slit experiment writ large. Light from a single source splits into multiple paths, travels around different sides of the lensing mass and reconvenes at the observer. If the paths have different lengths, and they almost always do, the light from different paths arrives at different times. But if the observer is clever, if the detectors are fast, the paths can be made to interfere. The photon that travels both routes simultaneously in the quantum sense can recombine at the telescope and produce the characteristic signature of wave interference. Or can it? Here is where the thought experiment meets the cosmos, where Wheeler's imagination met the accidents of astrophysics. Because a photon that travels around both sides of a gravitational lens has a history, or rather, it does not have a history, in exactly the sense Wheeler spent his career trying to articulate. It left the quasar billions of years ago. It entered the region of curved space-time around the lensing galaxy. It took both paths, or one path, or neither, depending on how you choose to describe it. And it has been travelling ever since, spreading out across the universe, its wave function evolving, its possible arrival points diverging and converging according to the geometry of space-time and the distribution of matter along its route. For all those billions of years, the photon had no definite path. It was not, in Wheeler's phrasing, a phenomenon. It was merely a smoky dragon, real at the tail where it was emitted and real at the mouth where it would eventually be detected, but undetermined, undefined, unobservable, along the entire length of its body. And then the telescope opens, the detector clicks, the measurement is made, and at that moment, according to the standard quantum formalism, the photon's history collapses into definiteness. It becomes a photon that took a particular path, that traversed a particular sequence of events, that has a particular story to tell. But which story? Which path? That depends on the configuration of the apparatus. That depends on whether the astronomer chose to combine the two images interferometrically, looking for wave behaviour, or to measure them separately, treating each as an independent particle arrival. That depends on a decision made 10 billion years after the photon left its source. Wheeler saw this. Wheeler understood that gravitational lensing was not just an astrophysical curiosity, but a cosmic realization of the delayed choice experiment on scales that no laboratory could match. He began to articulate this vision in lectures during the early 1980s, first at Princeton, then at Santa Barbara, then in a series of papers and presentations that would continue until the end of his life. The 1983 lecture introduced the phrase that would define his later cosmology: the self-excited circuit. The image is strange and requires unpacking. Wheeler imagined the universe not as a passive container for events, but as a participatory system in which observation and existence were intertwined. The universe, in this picture, brought observers into being through the ordinary processes of cosmic evolution. Stars formed, planets cooled, chemistry complexified, life emerged, minds developed, telescopes were built. And those observers, by the act of observing, participated in bringing the universe itself into being, not in the sense of creating matter ex nihilo, but in the sense of determining what had happened. The observer is produced by the universe, and the universe is given definite history by the observer. The circuit closes on itself. The snake eats its tail. This sounds mystical, and Wheeler was aware of the danger. He was not claiming that consciousness creates reality in some New Age sense. He was not claiming that the moon doesn't exist when no one is looking at it, at least not in any simple way. What he was claiming was more subtle and in some ways more radical, that the past does not have a definite content until that content is recorded in the present, that the question, which path did the photon take, does not have an answer until an apparatus is configured to answer it, and that this indeterminacy extends backward in time not as a metaphor but as a physical fact. The photon travelling for billions of years around a gravitational lens does not have a path during those billions of years. It acquires a path only when the measurement is made. The present, the configuration of the telescope, the choice of the experimenter, the click of the detector, reaches backward through cosmological time and determines retroactively the history of the photon. This is what Wheeler meant by observer participancy. This is what he meant by the participatory universe. And this is why the delayed choice experiment scaled up to cosmological dimensions was not merely a curiosity, but a probe into the foundations of reality. The experiment would test whether the retrocausal effect was real across billions of years. If it was, then the implications were staggering. The history of the universe, the actual physical history, the sequence of events that led from the Big Bang to the present moment, would not be fixed. It would be, in a precise and measurable sense, open. Not open to change by human will, not open in the sense that we could rewrite the past, but open in the sense that the past does not have a definite content until the present gives it one. The 10 billion year journey of the photon would be genuinely undecided, genuinely indeterminate, until the moment the astronomer chose how to measure it. Wheeler articulated this most clearly in a 1984 paper, reiterating his 1978 proposal and extending it to the cosmological domain. He quoted himself, "No elementary phenomenon is a phenomenon until it is an observed, registered phenomenon." And he applied this principle directly to gravitational lensing. "We ourselves get radiation today from the very early days of the universe," he wrote. "We can say, this observer who was brought into existence by the universe has, by their acts of observation, a part in bringing that universe itself into being." The sentence demands careful reading. Wheeler is not claiming that humans created the Big Bang. He is claiming something more nuanced, that the content of the Big Bang, the specific events, the specific photon paths, the specific histories, is not fixed until observers record that content. Beginning with the Big Bang, the universe expands and cools. After eons of dynamic development, it gives rise to observership, and acts of observer participancy, via the mechanism of the delayed choice experiment, in turn give tangible reality to the universe not only now, but back to the beginning. This was the vision. This was the conceptual stake. The photon's 10 billion year history is, on this reading, genuinely undecided until the moment of measurement. Not undecided in the sense that we don't know which path it took. Undecided in the sense that there is no fact of the matter, no objective truth, no answer waiting to be discovered. The question has no answer until the apparatus provides one, and when the apparatus provides one, it provides it retroactively, reaching back through the entire history of the photon's journey and selecting, from the cloud of quantum possibilities, a single, definite past. Wheeler knew this would be difficult to accept. He knew that it violated intuitions about time and causality that ran deep, intuitions that even physicists trained in quantum mechanics found hard to surrender. He knew that Copenhagen had provided a refuge from these implications, a way to declare the question meaningless and move on. But he also knew that the question was not meaningless. The delayed choice experiment made it precise. The gravitational lensing of quasar light made it testable, and if the experiment were performed, if the cosmic version of the delayed choice apparatus were actually built and operated, the result would either confirm or refute the most radical interpretation of quantum mechanics ever proposed. Wheeler did not live to see that experiment performed. He died in 2008, still waiting, still insisting, still pushing the physics community to confront what it had spent decades avoiding. The technology was advancing, the loopholes were being closed, The theoretical framework was being refined, but the cosmic test, the measurement of quasar photons that had travelled billions of years around gravitational lenses, the definitive proof or refutation of cosmological retrocausality, remained beyond reach. Beyond reach, that is, until a new generation of physicists took up the challenge, until telescopes and detectors and random number generators advanced to the point where the cosmic interferometer could be read. Until someone decided to point a telescope at a gravitationally lensed quasar and ask, once and for all, whether the present shapes the past. The seeds Wheeler planted were waiting. The question he asked was waiting, and the photons themselves, emitted from the hearts of supermassive black holes and bent around the curved space-time of intervening galaxies, were waiting to reveal whether their billion-year journeys had a definite history, or whether that history, like everything else in the quantum world, existed only in the moment of its observation. The waiting was not passive. In laboratories across 3 continents, in the pages of journals and the margins of conference proceedings, in the quiet hours when physicists stared at equations and tried to understand what they actually meant, the question Wheeler had posed was being turned over, examined, contested. Because the delayed choice experiment was not merely a puzzle to be solved, it was a knife. And depending on which interpretation of quantum mechanics you brought to the table, that knife cut in radically different directions. Begin with Copenhagen, the interpretation that had dominated physics since the 1920s. Niels Bohr and Werner Heisenberg had constructed it in the white heat of quantum mechanics' birth, when the equations were new and their implications were still being mapped. Copenhagen offered a bargain. You could use the mathematics without worrying about what it meant. The wave function was not a physical wave. It was a calculational tool. Superposition was not a statement about the world. It was a statement about our knowledge. A measurement was not a physical process that needed to be explained. It was the moment when probabilities became actualities. Full stop. No further questions. Under Copenhagen, Wheeler's delayed choice experiment posed no philosophical problem at all. Or rather, it posed a problem that Copenhagen declared out of bounds. To ask whether the photon really took one path or both paths was to ask a meaningless question. The photon had no definite history before measurement, not because that history was unknown, but because the very concept of history applied only to measured events. The past, in Copenhagen's austere ontology, was nothing more than the collection of records that existed in the present. There was no ghost of an unobserved trajectory haunting the beam splitter. There was no fact of the matter to be retroactively determined. There was only the click of the detector, the mark on the film, the bit of information registered in the apparatus. Everything else was interpretation projected onto silence. This was the position that had frustrated Wheeler for decades. It was not that Copenhagen was wrong exactly. It was that Copenhagen refused to engage. The founders had drawn a line and declared that questions beyond it were not physics. But Wheeler saw the delayed choice experiment as proof that the line was in the wrong place. The experiment forced you to confront the relationship between observation and reality. It demanded that you explain how a measurement made now could be correlated with a trajectory begun long ago. And Copenhagen's response, that there was nothing to explain because there was no trajectory until there was a measurement, struck Wheeler as evasion rather than explanation. But Copenhagen was not the only game in town. In 1957, a young physicist named Hugh Everett III had proposed an alternative so radical that it took decades for the physics community to take it seriously. Everett had been Wheeler's student at Princeton. He had watched his advisor struggle with the measurement problem, with the question of why wave functions seemed to collapse, and what observation actually meant in physical terms. And Everett had proposed a solution that eliminated collapse entirely. In Everett's framework, later called the many worlds interpretation, the wave function never collapses. When a quantum system encounters a measuring device, the system and the device become entangled, and the universe splits into branches, one branch for each possible outcome. The photon does not choose a path when the beam splitter is inserted or removed. Instead, both outcomes happen, but they happen in different branches of reality that can no longer communicate with each other. The observer who sees interference and the observer who sees which path information are both real, both exist, both have measured the same photon, but they exist in parallel universes that have diverged at the moment of measurement. Under many worlds, the delayed choice experiment takes on a different character. There is no retrocausality, no reaching back through time to determine a past event. Instead, the experiment reveals the branching structure of reality itself. When the experimenter decides whether to insert the second beam splitter, they are not choosing the photon's past. They are choosing which branch of the universe they will find themselves in. The photon took both paths in some branches and one path in others. The measurement simply sorts the observers into the appropriate branches. The past is not open, it is multiple. Every possible history has already happened, is happening, will happen, in some branch, somewhere, forever. This interpretation had a certain mathematical elegance. It preserved the linearity of quantum mechanics, avoided the mysterious collapse postulate, and offered a clear physical picture of what was happening during measurement. But it came at a cost that many physicists found too high: an infinite proliferation of unobservable parallel universes, each as real as our own, branching every time a quantum event occurred anywhere in the cosmos. The cure, some argued, was worse than the disease, and there were other interpretations, other ways of understanding what the delayed choice experiment revealed. The de Broglie-Bohm theory, also called pilot wave theory, offered a framework in which particles always had definite positions and definite trajectories. The apparent indeterminacy of quantum mechanics was not fundamental. It arose from our ignorance of hidden variables that guided the particles along their paths. Louis de Broglie had proposed the basic idea in 1927. David Bohm had revived and extended it in 1952. And under this interpretation, the delayed choice experiment told a very different story. In pilot wave theory, the photon always takes a definite path through the apparatus. There is no superposition of trajectories, no ghostly presence in both arms of the interferometer simultaneously. Instead, the photon is guided by a pilot wave, a real physical wave that propagates through the apparatus and determines via precise mathematical laws which path the particle will follow. The wave goes through both arms, the particle goes through one, and the configuration of the apparatus, whether the second beam splitter is present or absent, affects the shape of the pilot wave, which in turn affects which path the particle takes. Here is the crucial point. In the Bohmian analysis of delayed choice, the photon's path depends on the configuration of the apparatus at the moment the photon arrives, not at the moment it enters. There is no retrocausality, no backward-in-time influence. The appearance of retrocausality arises from our ignorance of the hidden variables, from our inability to track the pilot wave as it guides the particle through the interferometer. When we insert or remove the beam splitter at the last moment, we're not reaching back into the past. We're shaping the present configuration of the apparatus, and the particle responds to that present configuration in a perfectly causal, forward-in-time way. Pilot wave theory thus dissolved Wheeler's paradox, but at its own cost. The theory required faster-than-light influences. The pilot wave updated instantaneously across all of space, which sat uneasily with relativity. It required accepting that particles had definite positions we could never measure, and it offered no advantage in terms of empirical predictions. It agreed with standard quantum mechanics on every testable question. For many physicists, this made it a philosophical curiosity rather than a serious alternative, but the interpretive landscape was still shifting. In the 1990s, the Italian physicist Carlo Rovelli proposed what he called the relational interpretation of quantum mechanics. Rovelli's framework was inspired by the relational structure of general relativity, where notions like simultaneous and at rest have no absolute meaning but depend on the reference frame of the observer. He applied the same logic to quantum mechanics. The state of a system, Rovelli argued, is not an absolute property. It is a relation between the system and an observer. Different observers can assign different states to the same system, and both assignments can be correct, relative to the information each observer has. Under the relational interpretation, the delayed choice experiment reveals something subtle about the nature of physical facts. The photon does not have an absolute history, a trajectory that is the same for all observers, recorded in some cosmic ledger. Instead, the photon's history is relative to the observer who measures it. For one observer, who inserts the beam splitter, the photon exhibits interference and must be described as having travelled both paths. For another observer, who removes the beam splitter, the photon arrives at a single detector and must be described as having travelled one path. Both descriptions are correct. Neither is more fundamental than the other. the apparent retrocausality is not a reaching back through time, it is a consequence of the relational structure of quantum facts. Rovelli's interpretation was elegant and philosophically sophisticated, drawing on ideas from Einstein and from the philosophy of science, but it too raised difficult questions. If facts are relative to observers, what happens when observers compare notes? How do we explain the consistency of the physical world, the fact that different observers measuring the same systems generally agree on the results? Rovelli had answers to these questions, technical answers involving decoherence and the structure of information. But the answers were subtle, and not all physicists found them satisfying. This, then, was the landscape of interpretation that Wheeler's delayed choice experiment illuminated. Copenhagen, with its refusal to assign meaning to unobserved events. Many worlds, with its infinite branching of parallel universes. Pilot wave theory, with its hidden trajectories and faster-than-light connections. Relational quantum mechanics, with its observer-dependent facts. Each interpretation accepted the predictions of quantum mechanics. Each agreed on what would happen if you actually performed the experiment. But each offered a radically different picture of what that experiment meant. And this is why the experiment mattered. Not because it would produce a surprising result. The result was not in doubt. Quantum mechanics had been tested too many times, too precisely, for anyone to seriously expect it to fail. The experiment mattered because it would force a confrontation. It would take the abstract debate between interpretations and ground it in concrete physical reality. It would provide data that, while not definitively ruling out any interpretation, would carry unprecedented epistemic weight. Consider what an astronomical version of the delayed choice experiment would accomplish. The photon's journey would span billions of years and billions of light years. The apparatus would not be a few meters of optical bench, but the curved spacetime around entire galaxies. The timescales would dwarf any laboratory experiment by factors of 10 to the power of 20. If the delayed choice effect persisted across such scales, if the correlation between measurement choice and photon behavior held when the photon had been traveling since before the Earth existed, the implications would be profound. For Copenhagen, such a result would confirm the interpretation's predictions but also heighten its mysteries. The refusal to speak of the photon's trajectory would now extend across cosmic time. The meaninglessness of unobserved events would have to be maintained for billions of years and trillions of kilometers. The conceptual cost of the interpretation would become harder to bear. For many worlds, the result would be expected and unproblematic. Branching is branching, regardless of scale. But the experiment might provide indirect evidence for the interpretation by ruling out hidden variable theories that predicted deviations from standard quantum mechanics at cosmic distances. For pilot wave theory, the cosmic experiment posed a challenge. The theory predicted that standard quantum statistics would hold, but the specific mechanism, the pilot wave guiding the particle, would have to operate across cosmological scales. Any deviation from quantum predictions would falsify the theory. Any confirmation would demonstrate its scope. For the relational interpretation, the cosmic experiment would be a test of whether relational structure held across arbitrarily large separations. The dependence of facts on observers would now span the history of the universe itself. The stakes, in other words, were not about which detector clicked. The stakes were about the nature of time, the meaning of observation, and the relationship between the universe and the beings who perceived it. Wheeler had understood this. He had spent the final decades of his life articulating it, refining it, pushing his colleagues to confront it. He had coined a phrase, observer participancy, to capture the idea that observation was not passive reception, but active participation in the creation of physical reality. And he had proposed, in one of his most famous formulations, that the universe might be built on information rather than matter. It from bit, he called it. Every physical quantity, every it, derives its ultimate significance from bits, from binary yes or no answers to questions posed by observers. The delayed choice experiment was the sharpest test of this vision. If Wheeler was right, then the choice of measurement basis, the decision to insert or remove the beam splitter, was not merely a selection of which property to observe. It was a participation in the construction of physical reality. It was an act that reached back through the photon's history and gave that history its content. The experimenter was not a passive observer watching events unfold. The experimenter was a co-author of the events themselves. but Wheeler had died in 2008 and the cosmic experiment remained unperformed. The laboratory tests had been conducted by Ali in 1986, by Jacques in 2007, and they had confirmed the predictions of quantum mechanics. But the laboratory tests left room for doubt. The timescales were short, the distances small, the philosophical implications easy to dismiss as extrapolation beyond the evidence. What was needed was an experiment on Wheeler's original scale, an experiment with photons that had travelled billions of years, an experiment where the choice of measurement basis was separated from the photon's emission by an interval so vast that any classical explanation would require influences travelling faster than light across the entire observable universe. The physics community knew what was needed. The question was whether it could be done. The challenge was multifold. First, there was the problem of the source. Gravitationally lensed quasars were rare, and the lensing had to produce images bright enough to detect individual photon properties. Second, there was the problem of the apparatus. A true delayed choice experiment required that the measurement configuration be set after the photon had begun its journey through the lensing system, which, in the cosmic case, meant after the photon had been travelling for billions of years. Third, and most difficult, there was the problem of the freedom of choice loophole. This loophole was subtle but devastating. Suppose you used a random number generator to decide whether to insert the beam splitter. The random number generator is a physical system governed by physical laws. In principle, its output could be correlated with the photon's state, not through any faster-than-light influence, but through a common cause in the distant past. If the photon and the random number generator shared a common history, then their apparent correlation might be due to that shared history rather than to genuine quantum indeterminacy. The delayed choice effect would be an artifact, an illusion created by hidden correlations. In laboratory experiments, this loophole was already difficult to close. You had to ensure that the random number generator's output was truly random, not determined by any physical process that could be correlated with the photon source. You had to ensure that the decision was made fast enough that no signal, travelling at the speed of light, could communicate between the photon and the apparatus. Vincent Jacques' 2007 experiment had made significant progress, but critics could still point to the possibility, however remote, that the randomness was not genuine. For a cosmic experiment, the loophole was even harder to address. The photon had been travelling for billions of years. Its emission was correlated with the state of the quasar, which was correlated with the state of the early universe, which was correlated with everything else. How could you generate a random number that was guaranteed to be independent of a photon emitted billions of years before the Earth existed? The answer, when it came, was audacious. You could use other astronomical objects as your random number generators. Objects so distant and in such different directions that their light cones did not intersect with the light cone of the lensed photon. Objects whose photons had been travelling on completely independent paths through space-time, paths that shared no common cause since the very earliest moments after the Big Bang. Quasars, in other words. Quasars at different positions in the sky, emitting light that could be detected on Earth, and used to set the configuration of the measuring apparatus. If the colour of a photon from Quasar A determined whether the beam splitter was inserted, and if Quasar A was far enough away, in a different enough direction, that its light cone had no overlap with the light cone of the lensed photon from Quasar B, then the freedom of choice loophole would be closed. The decision would be determined by events that were, in the technical sense of general relativity, space-like separated from the emission of the photon being measured. No signal, no influence, no common cause could connect them. The correlation would have to be genuinely quantum mechanical. This was the approach that a new generation of physicists began to pursue. The idea had been in the air since Wheeler's original proposal. He had hinted at it in his papers, suggested it in his lectures, encouraged his students and colleagues to think about it. But the technology to implement it, the telescope sensitive enough to detect quasar photons with sufficient precision, the electronics fast enough to switch the apparatus in microseconds, the theoretical framework to analyse the results, had taken decades to develop. By the mid-2010s, the pieces were finally coming together. Experiments on Bell inequalities had shown that quantum correlations could be tested with photons from astronomical sources. The cosmic Bell test, as it was called, had been performed by multiple groups, using starlight and quasar light to close the freedom of choice loophole for entanglement experiments. The results had confirmed quantum mechanics, ruling out large classes of hidden variable theories. And the techniques developed for these experiments, the fast switching, the precise timing, the careful analysis of light cones, could be adapted to Wheeler's delayed choice scenario. The question was no longer whether it was possible. The question was when, and by whom, and with what results. On a rocky outcropping in the Canary Islands, 2,400 metres above the Atlantic Ocean, the William Herschel telescope sat in its dome, its 4.2-metre mirror polished to nanometre precision. The telescope was one of the world's premier instruments for optical astronomy, operated by an international consortium and used for observations ranging from distant galaxies to nearby exoplanets. Its location, on the island of La Palma, above the temperature inversions that created stable air and dark skies, made it ideal for precision measurements of faint objects. And in 2017, a collaboration of physicists prepared to use it for an experiment that would have astonished its designers. They were going to close the freedom of choice loophole for a Bell test by using photons from quasars billions of light years away. Quasars whose light had been travelling since long before the Earth formed, whose emissions were separated from each other by cosmological distances, whose photons could serve as the ultimate random number generators. The experimental team included researchers who had spent years on this problem. They understood the loopholes, the technical challenges, the theoretical subtleties. They had designed an apparatus that could detect photons from two distant quasars and use the colour of those photons, red or blue, above or below a threshold wavelength, to set the measurement basis for a Bell test. The quasars were chosen for their positions in the sky, their brightness, their distances. They were billions of light years away, in opposite directions from the telescope, ensuring that their light cones had not intersected since the universe was less than 100,000 years old. Before there were galaxies, before there were stars, when the cosmos was still a hot plasma of particles and radiation. The setup was exquisite. Photons from the two quasars would arrive at the telescope, be split by optical systems, and be detected by separate instruments. The colour of each quasar's photons would determine in real time how the measurement apparatus was configured, and the Bell test would use entangled photons generated locally at the telescope site, measuring their correlations in bases set by the ancient light from across the universe. When the data came in, it matched the predictions of quantum mechanics exactly. The correlations violated the Bell inequalities by a statistically overwhelming margin. The freedom of choice loophole, the possibility that the measurement settings were correlated with the hidden variables through some common cause in the past, was pushed back to the first moments after the Big Bang. If there were a hidden variable theory that explained the results, it would have to involve correlations established before the universe was 100,000 years old, correlations that had persisted through billions of years of cosmic evolution and somehow arranged for specific photons from specific quasars to arrive at specific detectors at precisely the right moments. No one believed such a theory was plausible. The cosmic Bell test had done what laboratory experiments could not. It had ruled out hidden variable explanations with a confidence that approached certainty. Quantum mechanics was vindicated. The strange, counterintuitive, seemingly impossible correlations that Einstein had called spooky action at a distance were real, verified by photons that had been travelling since before the solar system existed. But the Bell test was not the same as the delayed choice experiment. Bell tests measured correlations between entangled pairs of particles, testing whether those correlations could be explained by classical hidden variables. Delayed choice experiments asked a different question: whether the choice of measurement basis could affect the past history of a single particle. The cosmic Bell test had closed one loophole. The cosmic delayed choice experiment had yet to be performed, and yet the techniques were transferable. The fast switching, the quasar random numbers, the precise timing, all of these could be adapted to a delayed choice setup. The question was how to configure the experiment, how to identify a gravitationally lensed source that could serve as the photon, how to ensure that all the loopholes were closed. The physics community was tantalized. Wheeler's vision was within reach. The seeds he had planted decades earlier were finally bearing fruit. The cosmic interferometer, nature's own apparatus built from the curvature of space-time itself, awaited its observers. The photons were out there, streaming through the void, bending around galaxies, carrying information about their origins and their journeys. They had been travelling since before the Earth existed, since before the Sun ignited, since before the Milky Way had formed its spiral arms. And somewhere, in a telescope dome on a mountaintop, or in a laboratory filled with optical benches and electronics, someone would point an instrument at the sky and ask the question Wheeler had posed 40 years earlier: does the present shape the past? The interpretations offered different answers. Copenhagen said the question was meaningless. Many worlds said both outcomes happened. Pilot wave theory said the past was always definite, just hidden. Relational quantum mechanics said the answer depended on who was asking. But the photons did not care about interpretations. The photons simply travelled, bent, interfered or did not, arrived or did not, carrying in their wavelengths and their detection times the raw data that would, perhaps, decide between the frameworks that humans had constructed to understand them. The urgency was mounting. The technology was ready. The conceptual stakes had never been higher. And somewhere in the archives of physics, in the papers and lectures and letters of John Archibald Wheeler, the great smoky dragon waited, its tail visible at the moment of mission, its fangs visible at the moment of detection, its body forever shrouded in the quantum mist. What happened in between? The next generation of physicists was about to find out. The word itself carries baggage. Retrocausality. Say it aloud and the mind conjures time machines, paradoxes, the killing of grandfathers before they sire children. Science fiction has colonized the territory so thoroughly that any serious physicist who utters the term must spend the first half hour of any conversation explaining what they do not mean. And so, we must begin there, at the boundary between what the delayed choice experiment actually demonstrates and what it cannot, by the laws of physics themselves, ever demonstrate. The distinction is subtle but absolute. Physicists who work in this field speak of two kinds of retrocausality, and the difference between them is the difference between a puzzle and a catastrophe. The first kind, call it weak retrocausality, or microscopic retrocausality, or simply quantum retrocausality, refers to correlations. It refers to the strange fact that when you analyse the results of certain quantum experiments, the mathematics works most elegantly if you describe some information as flowing backward in time. The photon's behaviour at detection seems to reach back and constrain what the photon was doing earlier. The correlations look backward. The statistics have a temporal asymmetry that, if you squint at them the right way, suggests that future measurements are shaping past events. But, and this is the crucial qualifier, these backward-looking correlations cannot be used to send a message. They cannot be harnessed to transmit information from the future to the past. They cannot tell you the outcome of tomorrow's horse race. They cannot warn your younger self to make different choices. They are, in a precise technical sense, uncontrollable. The correlations are visible only after you have gathered the data from both ends of the experiment, only after you have compared the detection results with the measurement choices, only in retrospect. While the experiment is running, while the photon is in flight, while the choices are being made, there is no signal, no channel, no causal arrow pointing backward that anyone could exploit. This is weak retrocausality. It is strange. It is counterintuitive. It violates the common sense notion that the past is fixed and the future is open. But it does not violate special relativity. It does not allow faster-than-light communication. It does not permit paradoxes. The universe remains, in a certain sense, safe. The second kind of retrocausality, strong retrocausality, macroscopic retrocausality, the kind that science fiction loves, would involve actual signals sent backward in time. It would mean that an event in the future could cause an event in the past in the ordinary everyday sense of causation, predictably, repeatably, exploitably. This kind of retrocausality would violate special relativity. It would create closed causal loops. It would allow information to arrive before it was sent. And it is precisely what the delayed choice experiment does not demonstrate. Cannot demonstrate. The structure of quantum mechanics, combined with the structure of space-time, forbids it. The correlations are there, visible in the data, crying out for interpretation, but the control is not. The experimenter can choose whether to insert the beam splitter, can choose which measurement to perform, but cannot use that choice to send a message to the past. The choice affects the correlations, but the correlations cannot be read until after the choice has been made and the photon has been detected. This distinction between correlations that look backward and signals that travel backward is the hinge on which the entire interpretive debate turns, and it is here that the delayed choice experiment finds its deepest significance. Because what Wheeler's thought experiment reveals, and what the laboratory implementations confirm, and what the cosmic version would demonstrate on the grandest possible scale, is that the universe admits the first kind of retrocausality even while forbidding the second. The past is not written until the present inscribes it, but the present cannot rewrite the past in a way that anyone could notice in advance. Hugh Price has spent decades thinking about these questions. A philosopher of physics, originally trained at Cambridge and later a professor at Sydney, before returning to Cambridge as the Bertrand Russell Professor of Philosophy, Price has been one of the most persistent advocates for taking retrocausality seriously, not as a wild speculation, not as a desperate last resort, but as a legitimate framework for understanding quantum mechanics. Perhaps even the most natural framework, once you abandon certain assumptions that seem obvious but may not be required. Price's argument begins with a simple observation. Physics is time symmetric. The fundamental laws, Maxwell's equations, the Schrödinger equation, the equations of general relativity, work just as well running backward as forward. If you filmed a collision between two billiard balls and ran the film in reverse, both versions would obey Newton's laws. The microscopic world does not distinguish past from future, and yet we experience time as having a direction. Causes precede effects. We remember the past but not the future. Entropy increases. This asymmetry is real, but Price argues that it is imposed on physics from outside by boundary conditions, by the thermodynamic arrow, by our own position as macroscopic beings embedded in a universe that began in a low-entropy state. It is not built into the fundamental equations, and here is where the argument takes its crucial turn. If we insist that causes must precede effects, if we build that assumption into our interpretation of quantum mechanics from the start, then the Bell correlations seem impossibly non-local. Two entangled particles, separated by vast distances, seem to coordinate their behavior instantaneously, faster than any light signal could travel between them. Einstein found this absurd, hence spooky action at a distance. Generations of physicists have wrestled with it, but Price suggests an alternative. What if we allow causes to follow effects, at least at the microscopic level? What if the future measurement settings constrain the past behavior of the particles, just as the past emission event constrains their future detection? If you allow this, if you drop the assumption that causation must run in one direction only, then the Bell correlations become local. The entangled particles no longer need to communicate faster than light. Instead, their correlation arises because both particles are constrained by both the past preparation procedure and the future measurement settings. The future reaches back, the past reaches forward, the correlations emerge from the intersection. This is what Price calls the retrocausal loophole in Bell's theorem. Bell proved that no local hidden variable theory can reproduce the predictions of quantum mechanics, but his proof assumed that the hidden variables were not correlated with the future measurement settings. If you drop that assumption, if you allow retrocausal influences, then local hidden variables become possible again. The price you pay is accepting that the future constrains the past. The price you pay is abandoning the intuition that what has already happened is fixed and cannot be influenced by what has not yet occurred. Ken Wharton, a physicist at San Jose State University, has developed these ideas into a concrete mathematical framework. Wharton argues that quantum mechanics should be understood as a Lagrangian theory, where the behavior of particles is determined by boundary conditions at both ends of their trajectories. In classical physics, Lagrangian mechanics provides an alternative to Newtonian mechanics. Instead of saying that forces cause accelerations moment by moment, you say that particles take paths that minimize a certain quantity, the action, calculated over the entire trajectory. Both formulations give the same predictions, but they suggest different pictures of reality. Newtonian mechanics suggests a universe that unfolds moment by moment, each instant causing the next. Lagrangian mechanics suggests a universe where the entire trajectory is fixed all at once, where the boundary conditions at both past and future determine the path in between. Wharton argues that quantum mechanics, properly understood, is Lagrangian in this sense. The strangeness of quantum behavior, the interference, the entanglement, the delayed choice effects, arises because quantum systems are constrained by both their preparation and their measurement, by both initial and final boundary conditions. In this picture, the past is not separate from the future. They are co-equal constraints on the present. The photon that travels from a distant quasar to a terrestrial telescope is not simply pushed by its emission and received by its detection. It is, in some sense, pulled by both ends of its trajectory at once. The measurement you perform today constrains what the photon was doing 1 billion years ago, just as the emission 1 billion years ago constrains what you can detect today. This is not metaphor. Wharton has worked out the mathematics. The retrocausal models reproduce the predictions of standard quantum mechanics, including the Bell correlations, while remaining entirely local. No faster-than-light influence is required. No action at a distance. Just a willingness to accept that the direction of time, the distinction between past and future, is not fundamental. The philosophical implications are vertiginous. If Wharton is right, if Price is right, then the photon from PKS 1413 plus 135 was never in a definite state as it travelled through the cosmos. Its path around the lensing galaxy was not determined when it was emitted. It was not determined when it passed the galaxy. It was not even determined when it entered the telescope. It was only determined when the measurement was performed, when the detector configuration was chosen, when the final boundary condition was fixed, and that determination reached backward, in a very real sense, constraining the photon's history across billions of years. But, and this is the key, you could not have known this in advance. You could not have looked at the photon halfway through its journey and predicted what the future measurement would reveal, because the future measurement had not yet happened. The retrocausal constraint was invisible until the experiment was complete. The past was open, genuinely open, not in the sense that it could have been different, but in the sense that it was not yet written. And the act of measurement was the act of writing it. This is the documentary's philosophical crux. Retrocausality is not time travel. It does not allow paradoxes. It does not let you change what has already happened, because what has already happened was never fully determined until you observed it. The past is not a fixed record that you could, in principle, access and verify. The past is a probability distribution, a cloud of possibilities that collapses into definiteness only when the present asks it the right question. Wheeler understood this before the language of retrocausality was developed. His great smoky dragon was exactly this image, a creature whose body is undefined, unknowable, unreal in the quantum sense, because no one has yet looked. The fangs and the tail exist because they have been observed. The body does not exist because it has not, and so we return to Wheeler's late career synthesis, the doctrine he spent decades developing and refining, the idea he introduced most forcefully in 1990 but had been circling since the late 1970s, it from bit. The phrase is deceptively simple, 3 words, each one common, the combination unforgettable. It, the physical world, the particles and fields, the space-time continuum, the stuff of which everything is made. Bit, a binary digit, a yes or no, a 1 or 0, the most basic unit of information. And the from that connects them, a claim about ontology, about what is fundamental and what is derived. Wheeler was asserting that physical reality emerges from information, that every particle, every field, every event derives its function, its meaning, its very existence from binary answers to yes-no questions, that the universe is, at bottom, not matter, but measurement. Wheeler articulated this vision in his 1990 paper, the culmination of a body of work whose initial statements had begun appearing in 1977. By then he was nearly 80, one of the most honoured physicists in the world, a man who had helped build the atomic bomb and named the black hole and advised generations of students who had themselves become leaders in the field. He had earned the right to speculate, and speculate he did, with a boldness that startled even his admirers. It from bit symbolises the idea that every item of the physical world has at bottom, a very deep bottom in most instances, an immaterial source and explanation, Wheeler wrote. That which we call reality arises in the last analysis from the posing of yes or no questions and the registering of equipment-evoked responses. In short, that all things physical are information theoretic in origin, and that this is a participatory universe. A participatory universe. The phrase captures everything Wheeler was trying to say. Not a universe that exists independently of observers, waiting to be discovered, not a clockwork mechanism that would tick on unchanged whether or not anyone ever looked at it. But a universe that requires participation, that is called into being by the act of observation, that has no meaning and perhaps no existence apart from the questions that conscious beings ask of it. The delayed choice experiment was Wheeler's evidence. If the present measurement could determine the past behavior of a photon, if the choice of detector configuration could retroactively decide whether the photon had travelled one path or two, then the past itself was not fixed. The past was participatory. The past was a story being written in real time, or rather in all times at once, by the observers who gathered the data and registered the outcomes. Wheeler's famous formulation captured the implications. The past has no existence except as it is recorded in the present. This is a statement so radical that even physicists who accept the mathematics of quantum mechanics often recoil from its implications, because the mathematics is one thing, equations on a page, predictions that can be tested, correlations that can be measured. The ontology is another. Wheeler was not merely saying that we cannot know the past except through present records. He was saying that the past does not exist except through present records. The distinction is the difference between epistemology and ontology, between what we can know and what there is. Wheeler was making an ontological claim. The past, he said, is not out there waiting to be discovered. The past is created, constituted, brought into being by the measurements that define it. And here the tension becomes unbearable, because there was, after all, a quasar. PKS 14-1/35, or whatever source the eventual cosmic delayed choice experiment might use, is not a human construct. The photons that stream from its accretion disk, bent by the gravity of an intervening galaxy, arriving at terrestrial telescopes after billions of years of travel. These photons were emitted before the Earth existed, before the solar system coalesced, before the Milky Way's spiral arms had fully formed. The light was on its way while the first prokaryotic cells were developing on a cooling Earth. The light was passing the lensing galaxy while fish were evolving into amphibians. The light was crossing the last billion light years while hominins were developing language and building telescopes. To say that this light, this ancient light, had no definite path until a 21st century experimenter chose a detector configuration, this seems not merely counterintuitive but absurd. Surely the photon was doing something for all those billions of years. Surely its trajectory was defined by the gravitational field it encountered, by the geometry of space-time it traversed. Surely the past was real. And yet the mathematics says otherwise. The mathematics says that if you set up the experiment correctly, the detector configuration you choose today will determine which kind of statistics you observe. Interference or no interference, wave-like or particle-like, both paths or one path. The mathematics says that the photon's behavior correlates with your choice, even though your choice was made billions of years after the photon began its journey. The mathematics says that the past, in this specific and limited sense, is open. Wheeler did not flinch from the implications. If anything, he embraced them. The participatory universe was not a regrettable consequence of quantum mechanics, something to be explained away or interpreted into insignificance. It was the point. It was what quantum mechanics had been trying to tell us all along, if only we had the courage to listen. The universe is not a machine. The universe is a participatory process. We are not passive observers of a pre-existing reality. We are participants in a reality that is being constructed moment by moment by the questions we ask and the measurements we make. But the scientific instinct rebels. There must have been a real photon, following a real path, governed by real physics. The quasar existed before anyone observed it. The galaxy lensed the light before anyone built a telescope. The photons were travelling through space while Earth was still molten, while the dinosaurs rose and fell, while ice ages came and went. How can the present reach back and determine what was happening then? The answer, if there is one, lies in the distinction between what is determined and what is defined. The retrocausal models suggest that the photon's trajectory was always going to be constrained by both its emission and its detection. The future measurement was always going to be part of the story, not because the future somehow pre-exists and reaches back. That would violate special relativity. But because the entire trajectory from emission to detection is the quantum object. We are used to thinking of particles as things that move through time, acquiring properties moment by moment, their histories accumulating like a tape recording. But quantum mechanics suggests that particles are better understood as four-dimensional objects, world lines rather than world points, their properties defined by their entire trajectories rather than by their instantaneous states. In this picture, the past is not rewritten by the future. The past and the future together constrain the present. The measurement today does not change what the photon was doing a billion years ago. Rather, the measurement today and the emission a billion years ago together determine what the photon was doing in between. There is no moment at which the photon's path is undefined and then suddenly becomes defined. The path is, in some timeless sense, always constrained by its endpoints. We simply cannot access the full constraint until both endpoints are realized. This is not easy to accept. It requires abandoning the picture of time as a river flowing from past to future, each moment solidifying behind us as we move forward. It requires accepting a block universe picture, where past, present, and future all exist on equal footing, where the distinctions we draw between them are perspectival rather than fundamental. It requires accepting that our intuitive sense of causation, of pushing and pulling, of events unfolding in sequence, is not the deepest truth about reality. And yet the experiments confirm it. The Bell tests, the delayed choice experiments, the cosmic versions that are now within reach, all of them tell the same story. Quantum correlations do not respect our intuitions about time. The future and the past are entangled in ways that classical physics never anticipated. The great smoky dragon's body is not merely hidden, it is not yet written. But the loopholes remain. Even as the experimental program has closed off one classical alternative after another, critics have pointed out that a few possibilities remain. The most troubling is superdeterminism. Gerard 't Hooft, the Dutch physicist who won the Nobel Prize for his work on the electroweak force, has been the most prominent advocate of this view. The argument runs as follows. All of the experimental tests of quantum mechanics, including the Bell test and the delayed choice experiments, assume that the experimenters are free to choose their measurement settings independently of the systems they are measuring. If I choose to insert the beam splitter or not, that choice is assumed to be uncorrelated with the hidden variables of the photon. If I use a quasar photon to determine my measurement basis, that quasar photon is assumed to be uncorrelated with the particles I am measuring. But what if these assumptions are wrong? What if the entire universe, from the Big Bang onward, is one vast correlated system, where the state of every particle is entangled with the state of every other particle, where the quasar photon and the laboratory photon and the experimenter's brain are all constrained by the same initial conditions? In such a universe, the apparent violations of Bell inequalities would be illusions. The correlations would not require faster-than-light influences or retrocausality. They would simply be built into the fabric of reality from the beginning. Everything that has happened, or will happen, would be determined by the initial state of the universe, the particular configuration of the Big Bang, the precise arrangement of matter and energy in the first moments after inflation. This is superdeterminism. It is, in a sense, the ultimate conspiracy theory. Not a conspiracy of humans, but a conspiracy of physics. The universe is arranged from the very beginning to produce outcomes that look like quantum mechanics without actually being quantum mechanical. The hidden variables exist, but they are correlated with everything else, and that correlation prevents us from ever detecting them. The response of most physicists is to reject superdeterminism as unfalsifiable and unparsimonious. If you're willing to accept that the initial conditions of the universe were fine-tuned to produce the exact correlations that would fool every experimental test of quantum mechanics, you are no longer doing physics, you are doing theology. The superdeterminist hypothesis cannot be tested, because any test would itself be part of the conspiracy. It explains everything by explaining nothing. But the loophole cannot be closed by argument alone. David Quasar, a physicist and historian of science at MIT, has devoted considerable effort to pushing the freedom of choice loophole as far back as possible. His work with Andrew Friedman and other collaborators has taken the cosmic Bell test to their logical extreme. If the quasar photons used to set measurement bases were emitted billions of years ago, then any superdeterminist explanation would have to involve correlations established billions of years ago. The conspiracy would have to stretch back nearly to the beginning of the universe. Quasar and Friedman's cosmic Bell project used quasars as random number generators precisely to address this loophole. The farther back the random number source, the older the light, the more extreme the conspiracy required to explain away the results. The mid-2010s experiments at the William Herschel telescope on La Palma, which used quasar photons to set measurement bases, pushed the required conspiracy back to before the universe was 100,000 years old. Any hidden variable theory that could explain those results would require correlations established in the first moments after the Big Bang, correlations that had somehow persisted through 13 billion years of cosmic evolution, through the formation of galaxies and stars and planets, through the evolution of life and intelligence, all the way to the precise moment when a particular photon arrived at a particular detector and a particular experimenter made a particular choice. No one finds this plausible. The superdeterminist loophole remains logically open, but it requires commitments so baroque, so far removed from anything that resembles a physical theory, that even its advocates struggle to present it with a straight face. The experimental program has asymptotically approached the limits of what can be tested. The remaining loopholes require conspiracies that extend to the structure of the entire cosmos, correlations that were established before matter as we know it existed, fine-tuning that makes the anthropic principle look modest by comparison, and yet the loopholes persist, at least as logical possibilities. The cosmic delayed choice experiment, when it is finally performed, will close some of them. If the measurement settings are determined by quasar photons, if the lensed photon has been travelling for billions of years, if all the timing and switching conditions are met, then the experiment will demonstrate, to whatever degree any experiment can demonstrate anything, that the present measurement determines the past behaviour of the photon, or rather, that the present and the past are co-determined, constrained by boundary conditions at both ends, correlated in ways that no local hidden variable theory can explain without invoking conspiracies stretching back to the origin of time. The physics community watches and waits. The techniques are ready. The conceptual stakes have been sharpened by decades of argument. Wheeler's vision, conceived in the late 1970s, elaborated through the 1980s and 1990s, defended until his death in 2008, is about to be tested on the grandest possible scale. The photons are out there, travelling through the void, bending around galaxies, carrying in their quantum states the answers to questions that have not yet been asked. And somewhere in the world, astronomers and physicists are planning the observation. They are identifying candidate quasars, calculating lensing geometries, designing detector arrays, writing grant proposals, debugging software. They are preparing to ask the question that Wheeler spent his life formulating. Does the present shape the past? Is the universe participatory? Is reality, at the deepest level, not matter but information, not substance but measurement, not being but becoming? The answers will not come easily. They will be buried in statistics, in error bars, in systematic uncertainties that must be painstakingly characterized and controlled. They will be debated, reanalyzed, replicated, extended. The history of physics is littered with results that seem definitive and later turned out to be artifacts, with experiments that closed one loophole only to reveal another. But the trajectory is clear. The classical alternatives are being eliminated one by one. The quantum picture is being vindicated, correlation by correlation, photon by photon. And the implications, for causality, for time, for the nature of reality itself, are slowly coming into focus. Wheeler's dragon stirs in its quantum mist. The fangs are visible now, sharp and clear, defined by billions of detection events. The tail is visible too, stretching back across cosmic time, anchored in the nuclear furnaces of distant quasars. And the body, the great smoky body that no one has ever seen, that perhaps cannot be seen, that exists only as a superposition of possibilities until the moment of observation, the body awaits its definition. The night is clear over La Palma. In the dome of the Isaac Newton group, the air holds that peculiar stillness that comes after midnight on a volcanic peak, 2,000 meters above the Atlantic. The Canary Islands lie scattered below, their lights dimmed by local ordnance. The better to let human eyes and human instruments pierce the darkness between stars. Inside the telescope enclosure, the temperature has been equalized with the outside air, a precaution against thermal turbulence that might blur the seeing. The dome itself has rotated to face a particular patch of sky, unremarkable to the naked eye, distinguished only by coordinates that point toward a gravitationally lensed quasar billions of light-years distant. The photon that will arrive tonight, if the atmospheric conditions hold, if the adaptive optics perform, if the quantum random number generator fires at precisely the right moment, departed its source when the universe was less than 4 billion years old. The Earth did not exist. The Sun had not ignited. The molecular cloud that would eventually collapse to form our solar system drifted in the outer reaches of a young and turbulent galaxy, and already the photon was on its way, carrying in its quantum state a question that would not be formulated for another 10 billion years. The apparatus waiting in the focal plane assembly represents the culmination of Wheeler's vision. It is, in essence, a Mach-Zehnder interferometer adapted for astronomical use. The same conceptual design that Wheeler sketched in 1978, scaled up and hardened for deployment at the focus of a 4-meter mirror. The beam splitter sits in its mount, ready to be inserted or withdrawn in microseconds. The detectors wait in darkness, their avalanche photodiodes cooled to suppress thermal noise, their timing circuits synchronized to atomic clocks. And somewhere in the electronics rack, a quantum random number generator, itself driven by the arrival times of photons from a different, uncorrelated region of the sky, stands ready to make a choice that, on certain interpretations, will reach backward across 10 billion years of cosmic history. The experimenters know what they are attempting. They have read Wheeler's papers, studied the laboratory demonstrations, analysed the cosmic bell test that preceded this work. They understand that what they are about to do has no classical analogue, no precedent in the entire history of science. They are preparing to ask a question about a photon's past, about whether it travelled one path or two around a galaxy that lies between its source and their detector, and they are preparing to ask that question billions of years after the journey began, nanoseconds before it ends. And they know that, according to standard quantum mechanics, the answer they receive will depend on the question they choose to ask. The telescope tracks silently across the sky, compensating for the Earth's rotation, keeping the lensed quasar centered in its field. The guide camera makes minute corrections, adjusting the mirror's shape to counteract atmospheric distortion. In the control room, screens display real-time data, the seeing conditions, the photon count rate, the status of every subsystem in the detection chain. The observers wait, watching numbers scroll across their displays, listening to the quiet hum of equipment performing at the limits of precision. And then a photon arrives. It registers first as a voltage spike in the avalanche photodiode, a cascade of electrons triggered by a single quantum of light. The timing circuit stamps the event with nanosecond precision. The data acquisition system logs the detector that fired, the exact moment of detection, the state of the beam splitter at that instant. And in that moment, in that interval shorter than the blink of an eye, something happens that has no name in classical physics. The beam splitter was in, the random number generator, consulting its stream of cosmic photons from a different quasar, had chosen at that instant to insert the optical element that permits interference. And the photon that had travelled for 10 billion years, that had curved around an intervening galaxy, that had existed in a quantum superposition of two paths separated by distances measured in thousands of light years. That photon arrived at a detector whose position was consistent with interference. It arrived where only an interference pattern could place it, where only a wave could go, where only something that had travelled both paths simultaneously could be found. Had the random number generator chosen differently, had it extracted from its stream of cosmic photons a sequence of bits that dictated removal, rather than insertion of the beam splitter, the outcome would have been different. The photon would have arrived at one detector or the other with 50-50 probability, revealing which path information, demonstrating particle-like behaviour. And on the interpretations that Wheeler spent his life defending, that alternative choice would have determined a different past. Not discovered it, determined it. The photon would have travelled one path, not two. It would have gone around one side of the galaxy, not both. Its 10 billion year history would have been different. This is the moment Wheeler imagined. This is the measurement he could not perform, the experiment he could only sketch in words and diagrams and appeals to future technology. Here, at 2 a.m, on a mountaintop in the Atlantic, the question he posed in 1978 receives its answer. Can one choose whether the photon shall have come through both of the slits, or only one of them, after it has already traversed the screen? The data say yes. The data say that the choice made tonight by a random number generator consulting photons from a different part of the sky has reached backward, or correlated itself, or co-determined, with events that occurred before the Earth existed. The language fails us because language was not designed for this. We have no verbs that conjugate properly across 10 billion years, no tenses that accommodate causation without temporal direction, no grammar for events whose properties emerge from their endings rather than their beginnings. Wheeler knew this. He knew that what the experiment reveals cannot be captured in the categories of classical thought, that the very attempt to describe it forces us to choose between pictures that are individually coherent and jointly exhaustive but mutually incompatible, wave or particle, one path or two, definite past or open past. The photon does not resolve the choice. The measurement does. What does it mean to say that the past is open? Wheeler was precise on this point, more precise than many of his interpreters realized. He did not claim that we can send signals backward in time, that we can alter events that have already occurred, that paradox or contradiction lurks in the quantum formalism. The openness he described was subtler, more radical in some ways, less dramatic in others. The past has no existence except as it is recorded in the present. This was his formulation, his encapsulation of what delayed choice reveals. The photon's journey, its trajectory, its path through the gravitational lens, its wave-like or particle-like nature, does not exist as a fact of the matter independent of the measurements that record it. The journey becomes definite only when it ends, only when an act of observation forces the quantum superposition to resolve into a particular outcome. This is not a claim about our knowledge. It is not a statement about the limits of human perception or the difficulties of measurement at cosmic distances. It is a claim about reality itself, about the ontological status of events that have no observational record. Wheeler argued, and the experiments support him, that it is wrong to attribute a tangibility to the photon in all its travel from the point of entry to its last instant of flight. The tangibility, the definiteness, the settled fact of what happened, these emerge at the moment of measurement and not before. The 10 billion years of travel through intergalactic space, the curving path around the gravitational lens, the quantum superposition of locations separated by the width of a galaxy, all of this exists, if it exists at all, in a mode of being that has no classical analogue. Wheeler called it potentiality. Others call it the quantum state. The mathematics is clear, even if the interpretation is contested. What is not in dispute is that the photon, until it is measured, cannot be said to have taken one path or the other, to have been a wave or a particle, to have done anything definite at all. The dome continues its slow rotation, tracking the next target. The data files grow, recording photon after photon, each one a separate instance of the cosmic delayed choice scenario, each one a confirmation of predictions made 40 years before. The statistical picture builds slowly, as it always does in quantum experiments. Not a single dramatic revelation, but an accumulation of events that, taken together, trace out the interference pattern or its absence, the wave-like behavior or the particle-like behavior, depending on the random choices made microseconds before detection. And as the night progresses, as the data accumulates, as the experimenters note in their logs the seeing conditions and the equipment status and the preliminary results, the philosophical stakes remain exactly what Wheeler said they would be. The experiment is not just confirming a prediction of quantum mechanics, it is testing a claim about the nature of time, about the relationship between past and present, about the role of observation in constituting reality. It is asking whether the universe has a fixed history, a definite past that exists independently of the measurements that probe it, or whether history is something that emerges, that is constructed, that depends in some irreducible way on the questions that observers choose to ask. The evidence points in one direction: the classical picture, the view that the past is fixed, that events occur whether or not they are observed, that the universe has a definite state at every moment of its history. The classical picture cannot accommodate what the experiment reveals. The correlations are too strong, the predictions too precise, the loopholes too thoroughly closed. Something is reaching across 10 billion years, correlating the behavior of photons with the choices of experimenters, linking emission and detection in ways that no local causal process can explain. Wheeler spent his last years contemplating what this meant for the universe as a whole. If delayed choice works, if the present measurement genuinely participates in constituting the past, then the entire history of the cosmos takes on a different character. It is not a fixed sequence of events stretching from the Big Bang to the present moment, a movie that has already been filmed and is merely being played back. It is something stranger, something more participatory, something that depends in some essential way on the observations that unfold within it. He called this observer participancy, and he meant it quite literally. The universe, on this view, is not complete without observers. Not because observers are necessary to watch it unfold, like an audience at a play, but because observers are necessary to make it definite, to force the quantum superpositions to resolve, to transform potentiality into actuality. The measurements that we make, here, now, in telescopes and laboratories and the retinas of our eyes, are not passive recordings of a pre-existing reality. They are active contributions to the constitution of that reality, acts of participation in the ongoing process by which the universe becomes itself. This language sounds mystical, and Wheeler was aware of the danger. He spent considerable effort distinguishing his position from idealism, from solipsism, from the various New Age appropriations that seized on quantum mechanics as license for any fantasy. He was a physicist, trained in the hardest traditions of the discipline, a contributor to the Manhattan Project, a coiner of terms like black hole and wormhole that have entered the common vocabulary. He did not believe that consciousness creates reality in any simple sense, that wishing makes it so, that quantum mechanics licenses magical thinking. What he believed was more subtle and more radical, that the universe is woven from billions upon billions of acts of observer participancy, that physical reality emerges from information, that the distinction between observer and observed cannot be maintained at the deepest level of description, it from bit. This was his formula, his attempt to capture in 3 words the lesson of a lifetime spent probing the foundations of physics. Every physical quantity, every it, derives its ultimate significance from bits, from yes or no questions, from measurements that force the world to declare itself. The charge of an electron, a bit. The spin of a nucleus, a bit. The path of a photon through a gravitational lens, a bit determined by a choice made 10 billion years after the journey began. The universe is not made of matter on this view. It is not made of energy or space-time or fields. It is made of information, of answers to questions, of measurements that constitute the reality they probe. Wheeler pursued this insight to its logical conclusion. If reality emerges from measurement, if the past is constituted by the present, if the universe is genuinely participatory, then the entire history of the cosmos must be understood as a process of self-creation. The universe brings forth observers. Observers make measurements. Measurements constitute the past. The past, so constituted, includes the conditions that gave rise to observers. The loop closes. The circuit is complete. Wheeler called it a self-excited circuit, and the image captures something essential about his vision. A universe that bootstraps itself into existence, that has no need for external observers or prior causes, that contains within itself all the resources necessary for its own constitution. The image is vertiginous. It inverts all our usual intuitions about time and causation, about the priority of the past over the present, about the independence of reality from observation. And yet the experiments point in this direction. The delayed choice results, the Bell correlations, the loophole-free tests with cosmic photons, all of it supports the view that the classical picture, for all its intuitive appeal, does not describe the world we actually inhabit. Quantum gravity researchers have taken notice. The holographic principle, which emerged from Wheeler's own work on space-time and information, suggests that reality may be encoded on the boundaries of regions rather than in their interiors, that space itself may emerge from entanglement, that the fundamental level of description involves not particles or fields but quantum information. The connections to Wheeler's program are not accidental. His insistence that physics must eventually confront the role of the observer, that measurement is not a merely practical matter, but touches the deepest questions about the nature of reality. That information is more fundamental than matter. These insights have proven prescient, more relevant now than when he first articulated them. The night ends. The telescope shuts down as dawn approaches, the dome rotating to its park position, the instruments powering down, the data files copied to servers for analysis. The experimenters leave the mountain, tired and exhilarated, carrying in their laptops the results of an experiment that Wheeler could only imagine. They will spend months analysing the data, checking for systematic errors, characterising the statistical uncertainties, preparing papers that will be scrutinised by referees and debated at conferences. The scientific process will grind forward, as it always does, turning raw data into published results, preliminary findings into established knowledge. And somewhere in that process, in the accumulation of bits that will eventually constitute the accepted record, the question that Wheeler posed will receive its answer. Or rather, it will receive the only kind of answer that quantum mechanics permits, an answer that is statistical, probabilistic, expressed in terms of correlations rather than causes, consistent with the formalism but resistant to interpretation in classical terms. The photon that travelled for 10 billion years, that curved around a galaxy, that existed in superposition until the final instant, that photon will become a data point, a contribution to a histogram, a piece of evidence in an ongoing argument about the nature of reality. Wheeler would have understood. He spent his life engaged in exactly this process, turning philosophical questions into experimental programs, translating metaphysical intuitions into testable predictions. He knew that the answers would not come cleanly, that every experiment would raise new questions, that the foundations of physics are not the kind of thing that can be settled once and for all. He pursued the questions anyway, with a persistence that outlasted most of his critics, with a conviction that the universe, properly interrogated, would reveal something profound about its own nature. What has it revealed? That the past is not fixed, or at least not fixed in the way we thought. That measurement is not passive, not a mere recording of pre-existing facts. That the present and the past are correlated in ways that no classical theory can explain. That the questions we ask shape the answers we receive. That the universe is participatory in some sense that we are still struggling to articulate. These are not small revelations. They touch the deepest questions that physics can address. What is real? What is time? What is the relationship between the observer and the observed? The photon from PKS 14 Thunderstone 1 Thretive, the one that departed 2.6 billion years ago, that curved around a Seyfert galaxy, that carried in its quantum state the potential for interference or witch path information, that photon has been detected. Its story has ended, or rather, it has been given an ending by an act of measurement, and yet the larger story continues. The questions that Wheeler raised are still open, still contested, still unfolding in laboratories and observatories, and the minds of physicists who puzzle over the implications of what the experiments have revealed. There is something fitting in this. Wheeler always insisted that physics is a process, not a product, that our understanding is provisional, that the universe is not a thing to be comprehended but a mystery to be explored. The delayed choice experiment, performed now at cosmic scales, confirms this intuition in the most dramatic possible way. The photon's journey is complete, but the meaning of that journey remains in progress. The data are in, but the interpretation is still being constructed. The past has been constituted, and yet the past, what it means, how it should be understood, what it implies for the nature of reality, is still being determined by the questions we choose to ask. This is Wheeler's legacy. Not a settled doctrine, not a final theory, not a complete account of the quantum world. Rather, a way of thinking, a set of questions, a conviction that the deepest truths about the universe are accessible to inquiry, and that the role of the observer cannot be eliminated from the description. The experiments that test his vision will continue, the interpretations will multiply, the arguments will persist, as arguments about foundations always do, because the questions are genuinely hard and the stakes are genuinely high, and somewhere in the night sky, more photons are travelling. Quasars blaze in the depths of the universe, their light bending around intervening galaxies, their quantum states carrying potential answers to questions that have not yet been asked. The universe is full of such photons, trillions upon trillions of them, each one a carrier of information, each one a potential participant in an act of observation. They will arrive at telescopes that do not yet exist, be measured by instruments that have not yet been designed, answer questions that have not yet been formulated. And in each case, according to Wheeler's vision, the present will participate in constituting the past, the observer will help make the reality observed, the universe will continue its long process of becoming. The self-excited circuit is not complete. It never will be. Wheeler understood this too. The universe is not a puzzle with a solution, but a process with a trajectory, not a machine with a final state, but a story without an ending. The photon's journey lasted 10 billion years, but the meaning of that journey extends into the future, into the observations yet to be made, into the questions yet to be asked, into the understanding yet to be constructed. The past is open because the future is open. The act of measurement constitutes reality because reality is still being constituted, still emerging, still dependent on the questions that observers choose to ask. And so, we end where Wheeler ended, not with an answer, but with a question. The photon has arrived, the data have been recorded, the past has been constituted in one particular way rather than another. But the larger question, what it means that the present participates in constituting the past, what it implies about time and causation, and the nature of reality, that question remains open. It will remain open as long as there are observers to ask it, as long as there are photons to interrogate, as long as the universe continues its strange and participatory process of becoming itself. The dragon stirs in its quantum mist, its form never fully visible, its body forever emerging from the measurements that define it. Wheeler is gone now, passed into whatever state awaits those who have ceased to observe. But his questions remain, as vivid and unsettling as when he first posed them, as relevant now as they will be in 1 billion years, when some other observer, in some other place, makes some other measurement and participates once again in the constitution of the universe. The dome is closed, the mountain is silent, and the photons keep travelling, carrying their quantum states across the void, awaiting the questions that will give them meaning.